Hi, everybody. Welcome to Regular Expressions, your new lifestyle with Joff Thayer. How are you
Best
today,
title
Joff? Yes,
ever. I'm doing pretty good today. I cannot complain. The sun is out. It's still too
yes,
chilly here on the eastern seaboard, but the sun is out, so I'm happy for that.
yeah. Has it been crazy with pollen down there too?
Oh yeah, allergy season
Oh,
is allergy season. So what can you
it
say?
is like there's just like because I'm a window opener. Like some people just like leave their AC on all the time. If it's nice outside, I have my windows open. So I've got like pollen all over everything in my house. It is,
Yeah, that's the way it goes. So,
yeah.
um, I love doing today's class. First of all, regular expressions is just a whole lot of fun, and I do it in a fairly generic way. In other words, we don't sort of focus too much on any one implementation of regular expressions. So this is a really fun, it's a fun day. This is one of my favorites. We got a good number of people today. I think we're topping 80. Is that correct, Megan?
I think it was actually like 85 or 86.
Yeah. So
Yeah.
that's a really good crowd. Uh,
Yes.
Looking forward to that. It's we're in pre-show banter right now, uh, just for the record. We haven't started anything yet, uh, and we'll start at the top of the hour, which is 12 noon Eastern time in the United States. What is that? +5 for UTC, roughly. So 5 p.m. UTC if you're in the UK. And looking forward to a fun few hours together. We'll probably run. I typically run about 3.5, sometimes right up to 4 hours. So the timing, it's going to depend, uh, just how we go. But with this larger crowd, we'll probably just uh, run it straight through. I'll be able to answer questions as we go a little bit as I can, but we don't want to get stuck too much either, otherwise it'll slow us down. So we'll sort of balance that best way we can. So I'm actually curious, of the 80 or so people, I know there's only a few of you online right now. A couple of things we should say, and we'll say them again as we get to the top of the hour. Don't ask your questions in GoToMeeting or GoToTraining. We're not going to be looking there. It's very important that you join the Discord channel and that you interact in the Discord channel with me or Megan, or if there's troubleshooting to do there. So I'm not going to be, and neither is Megan, and folks, we're not really going to be paying attention to the GoToTraining panel. We don't look for questions over there. We look for them in the Discord. So that's important to know. And having said that, and we'll say it again towards the top of the hour, I am curious where people are tuning in from today. I'm always curious about that. Sure, we have a good number of you in the States. Hopefully, we have a few in Europe, and even more so if we have some in Southeast Asia. That would be terrific. Very excited this year because I get to visit Australia and go see some family in September. So it'd be fun if anybody from Oz or New Zealand is here. Yeah, just why don't you in the Discord just type in where you're tuning in from. You can just put in the state of the US or city state. You can put in a city state from wherever else you might be tuning in from, and let us know. Oh, look, we have Costa Rica. We have Canada. Okay, well,
Pennsylvania.
Pennsylvania, very
I'm
good. Costa Rica
Joff.
is convenient because the time zone is awfully close to us. Well,
Yes. That
uh,
always just is so weird thinking to me. I always think that they should be like Pacific time or something. I don't know why.
yeah,
But
longitude. There's a bend in
yeah,
South America.
yeah, I know. I always
That
think of
does
it
change
as like straight. Yeah.
things.
Yes.
So fun stuff. Yes. We have somebody from Kansas City, Missouri. Yes, love it. Went through Kansas City years and years ago. Decided to get in the car and just drive to the middle of the country just for fun. It did end up in Kansas City, of all places. So I've been there.
Did you end up?
Hey, there's somebody from Vienna, which is Austria, not Australia. By the way, on that Threat Cat, kind of funny thing happened to me years ago. I was in Innsbruck, Austria, and I was going up on the chairlift there up the mountain right behind Innsbruck. And at the bottom of the mountain, they were selling tourist shirts with kangaroos on them that said, "This is Austria, not Australia," or words to that effect. It was very funny. So, and it is actually kind of interesting to listen to some of the questions in the States that I've got over the years. Where people have said, "Well, do they speak English in Australia?" And I'm like, no, you're thinking of Austria, not Australia. So do that translation. So kind of fun. But I have to say, I have the most gorgeous photo of snow-covered mountains in the Alps there from Austria for the time I was there briefly, which was a really great memory for me. So very good. So welcome.
Yes, welcome everybody.
Supremo is typing.
Yeah. This is actually not the content. If you're new to anti-siphon training, this is what we call pre-show banter. We show up early because you show up early. You show up early because we show up early. It's this vicious cycle that we just keep repeating because it's fun. And plus we get to hang out and talk to everybody. And Joff and I get to hang out, which is always fun.
Yeah, we're just basically hanging out. We could even look at some hacker news. Let's see.
Yes,
I'll pull up the news for today. All right. Oh, this is fun. Google Project Zero detects a record number of zero-day exploits in 2021. I guess they're adding up the results of 2021. How about that? Oh, this is also a fun story. Researchers detail a bug that could paralyze Snort intrusion detection systems. Yes, IDS is still out there in the form of Snort, and now maintained by Cisco. The IDS has always been out there for a very long time. Apparently, there's an integer overflow issue that causes the Snort Modbus preprocessor to enter an infinite while loop. Yeah, that's called a denial of service for your Snort IDS sensor. So that would be a bad thing.
Yeah.
Just fun and games. Looks like Bugs Bunny just soared through the bottom of Alabama and Georgia and let Florida float out to sea. So we've been wondering if that's going to happen for a long time. But anyway, we've also wondered that about California sometimes, whether the San Andreas fault will finally just separate California from the United States. So anyway, good times. Without making any jokes one way or the other, that is a fun graphic.
That is fun.
So I do know we have somebody from the UK on board. Hopefully we have a couple of folks in Central Europe as well. We already know Austria is represented. I expect Germany will be represented as well, normally is at some point. Maybe Belgium will be represented as well. It's always fun to have some of our European friends along with us for these events. I have a great deal of fondness for Europe. I spent quite a number of years traveling around there when I was a SANS instructor, teaching in Sweden, Germany, UK, Czech Republic. So I look forward to coming back at some point. In fact, I'm hoping to go to a conference in Europe somewhere in the next couple of years. COVID
conferences
allowing, right? So
yeah.
That's a lot of fun.
So speaking of conferences, I wanted to let everybody know that there is still time to register for Way West, which is coming up in San Diego. The conference itself is the 4th through the 6th, but there is pre-conference training the 3rd and 4th. So we're really excited. We're going to be back in person, which I just cannot wait. But we will also, for those of you that are unable to join us in person, it will be virtual as well. So I think that that's just a component that we're going to keep with our conferences so that people can come and hang out with the Wild West Hackenfest crew, which is always a blast.
And we'd love to see you, of course. Well, the rest of the crew would. Unfortunately, I won't be able to be in San Diego, but if you're thinking about a conference, I couldn't imagine a nicer location in the United States to go visit. So definitely highly recommend going to Way West in San Diego. I think that's going to be a lot of fun.
Yes.
Tio Supremo asked, good morning, will this be a lecture only or will there be labs? Well, sort of both, mostly lecture, and the lab content that I'll do will be in the form of most of demonstrations, right? There's no actual hands-on for you. However, I will be uploading a zip file right before we get started into the resources channel. And that zip file contains the actual sample scripts and content that I will demo as I talk through it today. So you'll have that available, but no, for the entire 4 hours today, you'll get to sit back and listen to me explain this stuff and take you through it, and you get to look at those examples, but there's no actual hands-on lab for you to do in this 4 hours. It's really not really enough time to do that. So given the format. We're going to be doing breaks today. I'll probably try to give a break around about on the hour, depending on how the lecture material falls, but it normally works out fairly well to give a 10-minute break getting towards the top of the hour. So we'll take that as it comes.
Yes, and for everyone joining us today, you will receive a certificate of completion for class today, as well as a feedback form. Please fill it out. Let us know any and all feedback. We use it. And the session will be recorded, and the recording will be posted in the resources channel, probably later this evening, if not by tomorrow morning. So you can go back through the material and content. And for those of you that are going to be joining us via the recording, that everything will be posted in the resources channel.
Well, you can't beat that. So that's a lot of fun. And this class actually is also available as an on-demand option. We have put that in the on-demand portal these days. So that is a recording of me doing the same thing, just so you know, as we're going to be doing today. Sometimes people like the on-demand option. Sometimes people just prefer to be here live with us as we actually do the material.
Yeah, the on-demand is really a cool new product that we offer. The community definitely asked us for it, so we decided to build it. So it is really, it's exciting that we've got that up and live on the website. So most of our classes will be available via on-demand. So if there's a class that you want to take and you don't see it there, we still have quite a few classes in development. So just kind of check back periodically for that.
Yeah, no, it's really, really good stuff that on demand is up and running. I'm very excited by it. I've got 2 of my classes up. This one, Regular Expressions, which is just a super fun class, and you guys are all going to find that out today. And then I've got a much more advanced course called Enterprise Attacker Emulation and C2 Implant Development, which talks a lot about malware, a lot about evasion, and a lot about some developing various loaders and C2 channels and you know, things like that. Really sophisticated, fun stuff.
EAE C2, right?
That's right. Oh my goodness, yeah. My nose.
Because that title is a mouthful.
Yeah, so I call it EAE C2, EIEIO, or you know.
Yeah, it trips me up every time.
Too many
Sometimes I'll come on and be like, welcome to today's, and I'm like looking around like, where am I? Like, what even class is this? So this one's good. He had the slide up for me and everything so that I could actually introduce the correct class. So that was nice. Thanks, Joff. Appreciate it.
Well, you know, we like to put on a class act around here and make sure are up to
Oh,
scratch. So, all right. So see, we talked about Snort. We can do a little other hacker news. Let's see. There's been Okta says they had a security breach by the Lapsus group. That's not fun, but they say that it impacted only 2 of their customers. Oh, 2 customers. That's pretty cool. Limited damage, like that. Oh, this is always fun. You know, how many times has print been a problem, right? Hackers exploiting recently reported Windows print spooler vulnerability in the wild. You know, if you think about print, device management in general, that's some really old code, you know, that's been around for quite some time. So it's not surprising that you see exploits popping up around things like printers, device drivers, that kind of thing from time to time when people have the ability to actually spend time looking at exploiting and researching those kinds of vulnerabilities. Oh, look, we have somebody in the UK. There's Annie85. Welcome, Annie85. And as you said, I will say good afternoon because it is mid-late afternoon there in the UK. It is good to have you aboard, and welcome. So, do we call the UK Europe anymore? I mean, you know, I know it's the whole EU thing. I call it Europe still. The last time I was in London was January of 2020. So
wow.
I did a teach in London, in the UK, just before COVID shut everything down, pretty much.
Gosh, it's so crazy to think about just like pre-COVID. Like I was thinking about it the other day because there was a story on the news about cruise ships going back, and I remember when it first started and they had that cruise ship just like parked off of like Oregon or state of Washington or whatever, and then people were just like trapped on there.
Yeah. So cruise ships are always fun, right? They're a floating vulnerability
I know.
petri dish. Is what I call a cruise ship.
Yes, it was like usually like some sort of like a stomach virus or whatever, but then this started, and I mean I remember when it first started thinking, oh, it's just probably one of those like rotavirus or whatever the other things, but gosh, man,
yeah, not so much.
What a freaking ride this has been, huh?
Anyway, we're you know, hopefully all of us starting to come out the other side of this.
Yeah.
Yes, it's been quite a couple of years, so we're I'm an optimist looking up,
Yeah.
looking forward, that things will be getting better if we could just stop a few of these wars from going on. But anyway,
right.
let's not go down that road.
Yeah.
All right, so good to have you on board, Annie, and Tim and Scarlett and all the people I'm seeing typing in Discord. This is not the real show. You are seeing pre-show banter right now, which just means we're just chit-chatting before we actually start things off. In approximately 12 minutes, we will kick off the actual show and start talking about the real deal. In fact, I'm going to go to Google and find my timer application here, so I can put a countdown timer on the screen, because that's actually kind of fun to do.
And I have posted in the chat the Discord server link for those of you that are in GoToWebinar. We don't use the chat in GoToWebinar. We use the chat in Discord. So please join. And if you can't redeem your role for whatever reason, you can send me a message just like Annie did and got her all set up for class.
Fantastic. All right, I'm going to set this for 11 minutes, and I'm going to start this. This will be our countdown timer before the beginning of class. And so we'll just set that up there, so it's pretty clear what's going on.
So I did want to talk a little bit more about Wild West Hackenfest because I'm just so freaking excited about it. So for those of you that don't know, Anti-Siphon Training was kind of born out of Wild West Hackenfest, where we would have some pre-conference training, and then we kind of spun off into our own training thing with COVID and everything else. So it's awesome for me because it actually got me over here because you guys started to get busy. So, and I've been here over a year now, so I just absolutely love it. But we went to Reno last year, and then everything kind of shut down again. But we are coming back to San Diego, and the conference theme is You Hacked My Battleship, which is going to be so fun. Rick has created some, I don't know if you saw the cutouts that he did, Joff, of the battleship.
I
Like
haven't seen it.
Oh,
I mean,
it's
my head always goes to, are we actually going to be able to hack a battleship? Because that would be way more fun.
yeah.
But
Well, I don't think they'll let us do that.
I don't think the U.S. Navy will let us do that.
We are having dinner on the USS Midway, which is an aircraft carrier there, museum. So that's going to be super fun. I suggested volleyball tournament because of Top Gun, but that kind of got squashed. I thought that there would be a
Well,
terrific
now, Megan, Top Gun is now a very old movie.
Hey, listen, but the second one, or it's not, the new one is coming out soon. I cannot wait for it.
Yeah, there is a new one, isn't it?
Yeah.
It got suspended or something. Production was for a while, but well,
Yeah.
it'd be great when it comes out. So
Yes. So I mean, but if you grew up in the 80s, like you had to have seen Top Gun. It was just an amazing, amazing movie.
good fun.
I definitely wanted to be a fighter pilot after that, but that didn't. There was the whole like military thing and like rules and stuff that that didn't work out as well. But I still like it's a total dream to go up in a fighter jet. That would be so cool.
Yeah.
Are you like a roller coaster person? Or are you?
Well, I'll just say that I was. I don't think that I could stomach being on a roller coaster today. Funny thing about becoming middle-aged is you tend to not deal with that kind of thing quite as well
Yeah.
as you do when you were younger. But I've certainly spent time on roller coasters and enjoyed them
Yes.
in the past, especially when my kids were little, which they
Yeah.
know.
We're pretty
Oh,
close.
Scarlett says my title of my show should be "Who Wants to Marry a Billionaire in Space?" Hey, we could have a reality TV show, and we just need to borrow, one of Elon or Jeff Bezos, rocket, and or even Virgin Atlantic, right?
Yeah.
What's his name?
Right.
It's slipping me.
Richard
Anyway,
Branson.
Richard Branson's rocket. So it's probably better off if we borrow Richard Branson's flying space plane, because then we could probably do a wedding ceremony, at great altitude,
Yeah.
a little bit easier. Or Bezos, I gotta tell you that I'm not going to say this publicly, but I'm going to infer. I'm sorry, but Jeff Bezos's device looks like a flying, what, in my opinion.
Yeah.
Anyway, it doesn't really have a cool factor to it, to my life. Okay, so we have 6 minutes to go.
Yes. On that note.
Before we blast off for regular expressions, your new lifestyle. You know why I call this by this particular title? And that is because with regular expressions, once you adopt it as a philosophy in some of the stuff you do in information security, it literally changes your life. And so what I'm hoping is for your life to be actually changed by this experience at some level. And if I achieve that today, I've achieved something that's really wonderful for us as a community, but it's also wonderful for you as an individual with your individual skill sets that you exercise daily in your IT careers, right? Tia Supremo points out, Bezos did take Captain Kirk into space. And yes, he did. And anybody who saw them come back down after that trip, what's the actor's name? William Shatner was absolutely speechless when he stepped out of that rocket. He didn't even have words to express his appreciation and the experience, which was quite an amazing thing.
I know, gosh, there's just so many things that are just so crazy to even think about. I mean,
well, I was hoping, so I called up my mate Elon. I said, Elon, look, I'm going to Australia later this year. Have you perfected that suborbital flight thing? Because I actually would much prefer to go up in the air and suborbital around the planet in a couple of hours or maybe less than flying the 24 hours of hell-raising flight that it takes to get across the Pacific Ocean. Turns out the Pacific Ocean is awfully big.
Yeah.
There's a lot of water. And so, yeah. Elon said, no, don't have that yet. Sorry, Joff, mate. You're going to have to take the regular jets. I said, oh, Elon, okay.
I wonder why.
Let my Tesla back.
I wonder why they remember the Concorde, was that just like too expensive for them to run, or why did they ever like get rid of that? Because that was a pretty short flight from the US to like the UK, wasn't it?
It was. You could do it in under 4 hours. The Concorde mostly was, as my understanding was terminated because of its aging technology. One, being very expensive to operate in terms of fuel cost, and see only limited demand in terms of the people that could afford the ticket, right? So that sort of combination made it not very economically viable. But people are still working on various options in supersonic flight, and there's a lot of people working on electric-based aviation, which I think is kind of fascinating.
Wow.
We'll see where all that goes. It's an interesting world we live in. All right, 3 minutes and 9 seconds.
Yes.
So excited.
If you need to do a bio break before class starts, go ahead and get that done. Just for those of you that are just joining us, this training has not started yet. The doomsday timer is there. No, it's not doomsday. It's the timer that is going to change. You're going to have a new lifestyle after this with regular sessions. So the session will be recorded. You will receive a certificate of completion. Usually, I think that we've been sending it out like right after class, so people have the class fresh in their mind so that they can fill out the feedback form. Please do that. For those of you that do fill it out, you're entered to win a t-shirt, the I Just Show for the Pre-Show Banter t-shirt, which is shameless self-promotion, but hey, we'll take it. It's a pretty scientific drawing. I give a number of people that filled it out to my 11-year-old, and he picks the winner between this and this, and that's how the winner is chosen. I don't go through and find the nice comments and only give that person a t-shirt. It is very scientific and a blind draw.
All right. So we got about a minute to go.
About a minute.
Welcome everybody who have come in more recent time on the countdown. I think we have now 36 attendees logged in, which is good to see. Should be a good fun time.
And I will be around in the background if anybody needs anything. I do have to hop over to a Hacking Cast, but then I'll be back. So if anybody needs anything, you can certainly send me a message on Discord. But I'm sure everything will move along swimmingly, but if there's any issues, yes. just ping me if you need me during the next hour or so. I'll be over on the Hacking Cast.
Sweet. Let's see, before I get started, I am going to drop a zip file into the resources channel here.
Yep.
And this contains a couple of cheat sheets plus some example stuff that we will talk about today. So I just wanted to throw that in there before we got kicked off.
Yep. Yeah, and it looks like we are pretty much up at the top of the hour. So I will let you take it away, and I will be back this afternoon, later this afternoon.
All right, sounds good. Thank you, Megan.
All right, have a good class.
Thanks. All right, everybody. So we're going to get started. Look, not that I don't mind you looking at me, but I'm going to turn the camera off because it's a little distracting, me looking at myself rather than focusing on the slide material. So you'll just hear my voice for the most part. I don't think the webcam is actually necessary. I might drop it on again right at the end, just before I say goodbye. But having said that, let's get started. All right. As I mentioned before, if you have a question for me, please put that in the Discord as we're proceeding. We will try to take breaks right around the top of each hour as we're going through the material. There is no specific hands-on lab with this class. There are examples and there are demonstrations that I will show you as we move forward. All right. And first malfunction is my clicker is not working. All right, let's double check. There we go. Now it is. All right. First of all, about myself, my name is Joff. I am a malware developer, researcher, pen tester with Black Hills Information Security. I'm a former SANS certified instructor of SEC 573, which is a Python class with the SANS Institute. I'm still a SANS certified instructor. I just don't actually teach anymore with them. I prefer to teach here with Anti-Siphon. Co-host also of Security Weekly podcast, which is on every week, Wednesday evenings, US Eastern Time, about 6 p.m. And that would be tonight. I may or may not be there because I'm teaching you guys today, so we'll see how that goes. Having said that, let's move into the material. First of all, I would ask you this: why would you learn about regular expressions? Well, let's just think about this. In the information security community, we spend a tremendous amount of time analyzing textual data. You know, if you think that you're not doing that, I don't believe you, to be honest. I mean, we are always looking through logs. We're always searching through things like SIM databases and event management systems, looking for interesting data as certainly defenders and as attackers. We're always looking for interesting data, especially if we're interested in exfiltrating that data from a network from the pen testing perspective. So having said this, why not do the process, if you like? Why not execute those actions of looking for data with more power? Why not up your game in terms of being able to search for data? And that's why you're here, right? Let's learn to love regular expressions, because for textual data analysis, regular expressions are really extremely useful. So what exactly is a regular expression? What it actually is a special text string that describes a search pattern which is used to search through some other textual data. And you will often see a regular expression abbreviated online as a regex or regex. You can say it a number of different ways, right? So where did this thing come from? Well, regular expressions are a technique that were developed in theoretical computer science a long time ago, as in 70 years ago, approximately, right? In the 1950s, a gentleman by the name, excuse me, spring allergies, of Stephen Cole Kleene formalized a description of a regular language for performing pattern matching of textual data. This was before computers were, really much out of the infancy stage of very large mainframes, right? Regular expressions are not a programming language. And this is an important point, but they are a pattern matching tool. So sometimes people think that regular expressions are a programming language, sorry. That is not the case. It is a description of a formal language to perform pattern matching. Regular expressions are everywhere in modern day computing. And one of the reasons that regular expressions are everywhere is that the early implementations of the Unix operating system adopted regular expressions as part of their architecture in terms of the pipelining and processing of textual data. So Unix text processing tools like VI, SED, awk, and grep all have regular expression support in them. We even have some search engines out there that have limited regular expression support. There are search features of software products, such as Sims, particularly, word processors, and the like, that have regular expression support. IPS or IDS signature development supports regular expressions commonly. There are multiple programming languages in the industry, such as C#, Golang, Java, Python, and probably many more that have implemented and support regular expressions. The Bourne Again shell, Bash, as well as ZSH or ZSH, whatever country you're from, does support regex as well. For the pen testers in the community, the Burp Suite interception web proxy supports regular expressions for some of the pattern matching functionality that you can use to search and replace text in web HTTP transactions, for example. So with the widespread adoption of regular expressions in all of the computing technology that we use, in all of this various swath of software, it's a good idea to know regular expressions. In fact, knowing regular expressions makes you the wizard. Right? You can see here an XKCD cartoon. Hey, everybody stand back. I know regular expressions, right? You can really accelerate your career by using regular expressions in your daily professional life. And when I say daily, for a good reason, I personally use regular expressions every day. I can pretty much say that. Yeah, I don't think a day goes by when I don't use a regular expression now, right? It's a very, very useful technology to be able to use. Now, fortunately or unfortunately, depending on whether your glass is half full, half empty, whatever, there are various flavors of regular expressions. POSIX was a standard defined in the 1980s, which introduced something called a basic regular expression, as well as an extended regular expression. These are abbreviated to BRE and ERE. Later in time, in the mid to late 90s, the Perl programming language introduced Perl-compatible regular expressions, and these are known as PCRE. And this was a C language library that was developed in support of the Perl scripting language. Now, the reason I mention this is there are differences between the pattern matching language in these two standards, essentially two standards. POSIX has things like character classes, which are expressed with square brackets and colon digit colon or colon alpha colon and so on. So the character classes, as we will learn as we get into the fundamentals of regular expression, are slightly different in the POSIX standard. You know, POSIX is BRE and ERE, right? POSIX, in its implementation, finds the longest of the leftmost match versus PCRE, Perl compatible, generally stopping on the first pattern match. PCRE additionally requires that the pattern, when you are matching, is typically enclosed by some sort of delimiter. And that's mostly because PCRE is built into a lot of programming language, and you're going to have programming languages, and you are going to have delimiters like quotes, single quotes or double quotes, around a regular expression there. So what are the real take-homes about the flavors here? Well, it's just this. PCRE or Perl-inspired regular expression support is normally found embedded in programming languages, and that's because the basis of PCRE is a C language library that could be and is incorporated into a lot of other programming languages. POSIX, on the other hand, is more common in Unix command line tools, well, because that's where all of this implementation first started. Unix adopted the POSIX standard to bring various flavors of Unix together and kept with the POSIX-based regular expressions at that particular time frame. Now, there's a useful gist out there on comparing some regular expression features, this gist is kind of interesting because it points out the various features in regular expressions and whether any particular implementation actually supports that feature. And sometimes things like this are very useful when you're working in, let's say, JavaScript or ECMA versus Ruby versus Perl versus Python, etc., to understand what's going on. Now, for the remainder of today, with the exception of a couple of slides here and there, we're going to mostly focus on Perl-compatible regular expressions, PCRE, right? It was written in 1997 to support the Perl scripting language. Not surprisingly, the syntax for PCRE regular expressions, it closely resembles Perl. Now, for those of you who lived through the years of Perl, which I did, just like in the C language, you could write a Perl script that absolutely nobody could read. Perl allowed you to express things in extraordinarily complex ways. So some people will say that regular expressions are sort of equally unreadable as Perl is. And that may be a true expression. We'll leave that for you to judge. The PCRE C language library is used in many large projects today, including things like Apache Nginx as well, R, PHP, Python, just so many things, right? PCRE has been incorporated into lots of other software projects, right? Of course, we wouldn't be the same unless we put another cartoon up here. If you're having Perl problems, I feel bad for you, son. I've got 99 problems, so I used regular expressions. Now I have 100 problems, right? Yeah, but after today, you're going to be like, no, you don't, because I know how to read and interpret those regular expressions. So let's get down to it. What is this regular expression pattern language, right? What does it look like? How are they processed? With regular expressions, everything, first of all, is a character. Constructing a regular expression means writing a pattern to match a specific sequence of characters in another bit of textual data. The pattern that we can construct, well, it can have exact matches, or it can include special meta characters to modify how we perform pattern matching. The different types of meta character enable various functionalities in the regular expression match, such as predefined or custom character set matching, such as quantifiers to match some count of characters, such as anchoring or asserting the beginning or the ending of a string to match, such as logical operators, for example, or even subgroup matching. Give me 1 second. I'm going to pause here and not sneeze into the microphone. So Tio Supremo asks on the Discord, which flavor of expressions does Kali Linux use? Well, that depends is the answer. In terms of the command line tools, such as sed, awk, grep, and so forth, it can probably use POSIX or PCRE syntax, right? So I think you will see as we go through it that things like Kali Linux, because there's such a big distribution of various pieces of software, incorporates both flavors of regular expression. It's Unix, right? One of my favorite analogies about regular expressions is they're very much like Pac-Man. Now, those of us in the X generation remember very clearly that video game of Pac-Man where the little Pac-Man character ran around consuming the dots on the screen, and your job was to consume all of the dots to clear off that screen and go on to the next thing. And you could get extra points by consuming things that allowed you to then consume the bad guys and things like that, right? Why this is a good analogy is because regular expressions perform successful matching of a pattern by consuming the data from left to right. Now, sometimes the implemented functions perform a single match of a pattern and sometimes multiple matches of the same pattern. This aspect is implementation dependent. Additionally, to succeed in matching, Pac-Man, as we'll call him, must sometimes backtrack. Sometimes he needs to spit out a few of the dots and reconsider how to properly match the pattern that is expressed. So that implies that the data that we're matching against is only consumed on a successful match as we process that string or textual data from left to right. Now, while we can perform exact matches with regular expressions, there are character sets or classes to match a range of different characters in a regular expression. For example, in the pattern definition, if we use \W, that allows us to match a single word character. Now, a single word character, by definition, is the letters A through Z uppercase, A through Z lowercase, digit 0 through 9, or the underscore. That is the definition of this character set. Okay. Similarly, a \D in a regular expression pattern will match a single digit. So these are, I like to think of these as predefined or built-in character classes, right? Or character sets. That's what we're talking about here. \S, as in Sam, is designed to match a single space character. This could be a space, a tab, or a new line by definition. Now, with some of these predefined sets, there's also an opposite version. \W, for example, matches a single character that is not in the \W set, i.e. anything that is not A through Z uppercase, lowercase, 0 through 9, or the underscore. Okay. Similarly, \D matches a single character that is not a digit. Okay, so this is a negation of the match. \S as well is a negation of the \S set, and that's a pretty wide set. Match anything that is not a space, or that's almost anything, right? There's another interesting character class in the PCRE character class list, and that is \b. This is considered a word boundary match. A word boundary is defined as the transition between what is a word character and what is not a word character, and vice versa. So you can see that this particular character set, the \b, is quite explicitly focused on parsing through sentences in a paragraph, for example, or sentences just in words just in an individual sentence, right? It's a word boundary match, right? We're splitting up words. These are your basic predefined sets. Now, what happens if you are writing a pattern match and none of the predefined sets are adequate? Let's say you want to create a custom set of your own. Well, you can do this using square brackets. If you use square bracket uppercase A dash uppercase F, for example, that defines a match for a single character that's in the range uppercase A through uppercase F, as in Freddie. So the dash has a special meaning here. You're defining a range of characters to match, but in this case, it's only 6 characters. It's A through F. Okay. Now, with a custom set, it is possible to define multiple characters that are not in a range, and it's even possible to include another set inside of a custom set. So, for example, square bracket \W lowercase, exclamation point, and the @ symbol, that means match a single character that's in this custom set, and within that custom set is a word character set, an exclamation point, a specific character there, and the @ symbol. So we now have extended, if you like, the original intent of the word character set by adding 2 more characters into our own custom set. Okay. Now, with custom sets, just like with the predefined sets, you do have the ability to negate a match, and that ability is provided to you by putting a caret symbol at the beginning of the custom set. So square bracket caret A dash Z uppercase, close the square bracket, that means match a single character that is not in the range of the letters A to Z or A through Z, right? And there's one other special character set, which is a very broad definition in regular expressions, and that is the dot or the period here in the States. And what the period or dot means is to match any single character. It's a wild card for match anything, but only one of them. Okay, match anything. All right, bear with me. We're building some base here, and we'll go into some examples in just a minute. Now, after any single match in your pattern definition, we can actually specify what's called a quantifier. And the quantifiers are defined exactly as follows. A question mark means match the previous character 0 or 1 time. The way to think of that is the question mark is an optional match. The star or the asterisk means match the previous character 0 or more times. Okay, so it can match absolutely 0, or you can match up to infinity times. The plus character is slightly different after a character in the pattern. That means match that previous character 1 or more times. All right. Now, what if you wanted to match something an exact number of times? Let's say you wanted to match, I don't know, 4 digits or something like that, where you can use curly braces around a quantifier to do this. So you could say curly brace and then some sort of number like 5 or something like that, and close the curly braces. That would mean match the previous character exactly 5 times if we used 5. Okay. Samuel, I see your question. Let's hold that until we look at some examples. Okay. Now, if we wanted to match the previous character between X and Y times, we could use curly brace X comma Y, close the curly brace. Let's say we wanted to match between 1 and 5 digits. We could say \D, curly brace 1 comma 5, close curly brace, right? All right. Let's look at a quantifier example. So how could we match a US North American numbering plan phone number? First of all, the North American numbering plan has exactly 10 digits, excluding the country code, for a typical North American phone number. And in those 10 digits, the first 3 are known as the NPA, which is essentially the area code. Then there is a single digit for the subscriber code in the local area code, followed by 5 more digits for the actual fully qualified phone number. We're excluding the country code for now. So how could we write a regular expression to match this, making the assumption that we have dashes between the groups of digits? Okay. Yes, this will be recorded and shared later if you cannot continue attending right now, Natty. So the regular expression without a quantifier could be expressed like this: \D, 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 dash, \D, 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 dash, \D, 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 i.e. match exactly 3 digits, followed by a dash, followed by another 3 digits, followed by a dash, and then followed by 4 digits. Unfortunately, that means your regular expression pattern is longer than it needs to be. And the reason is we can use quantifiers to shorten that regular expression. We know that we're going to match 3 digits, so we could say \d curly brace 3 close curly brace, and the quantifier comes right after the character to match, so that means match exactly 3 digits, followed by a dash, followed by another 3 digits, \d curly brace 3 close curly brace, followed by a dash, followed by exactly 4 digits. And so that is an example of how to construct a regular expression for a North American numbering plan phone number using the quantifiers in the curly braces. Now, these quantifiers that I'm talking about can sometimes be greedy, and greediness can be a problem for us in our pattern matching sometimes when we are trying to extract more discrete groups of data. In particular, the plus and the star quantifiers, well, they can be very greedy because this really means 1 or more or 0 or more of the prior character. And if, for example, the prior character is a dot, that would mean 1 or more of anything, or 0 or more of anything if we did dot star. Now, in some circumstances, a regular expression can backtrack to satisfy a pattern. Okay? Example below. Dot plus in a pattern definition would consume everything to the end of the data. That is 1 or more of any possible expression. So if the data is what a nice tree, and we have dot plus and the word tree in the pattern, well, the regular expression does have the ability to back up and satisfy the tree part of the pattern if it needs to. That's Pac-Man essentially spitting out the characters again and backing up to give that exact match for tree. All right, so you're all sitting there thinking, okay, Geoff, that's cool. The quantifiers can be greedy, but why do I care, right? Why do I care if the quantifier is greedy? Well, we care because there are certain situations when we don't want to be so greedy in our pattern matching. Let's have a look at when being really greedy is not helpful. Here's a scenario for you. Imagine if you want to extract multiple sentences from this paragraph of data. So the data is, I love the sunlight in the spring. It makes me feel so alive. Please don't let it rain. Well, first of all, we need to define the rules of what exactly is a sentence. Well, the rules will be as follows. A sentence begins with a capital letter. A sentence ends with a punctuation character. And to make it easy for ourselves, we will define the punctuation characters as exclamation point, question mark, and a dot or a period. And then any letter can be in between that capital letter and the punctuation character at the end. So having defined what a sentence is, in red here is one possible regular expression to match sentences. We have a custom set, match a single character in the range of letters A through Z in uppercase. Okay, that fits that a sentence must begin with a capital letter. Then use dot plus to match all of the stuff in between the final character, which will be a punctuation character, exclamation point, question mark, or the dot. Now we have to use escaping in front of the dot because the dot has special meaning normally, in that a dot would be matching any character. When we say \dot, we're actually telling the regular expression code, no, I want you to match exactly the dot. Okay. Now, what is the greediness problem? What am I trying to get at here? Well, if you typed in this regular expression into a regular expression pattern matching engine, and then you provided the sample data, and I did exactly this on a web service called regex101.com, the challenge is you would not get 3 distinct sentence matches. The dot plus would be greedy and continue to consume all of the data up to the very last punctuation, giving you only a single match. If our original goal was to extract individual sentences, we have not met the goal. We're being too greedy with our matching. So we need to tell regular expressions, hey, stop being so greedy. There is a modifier right after the quantifier that allows us to tell regular expression engines to stop being so greedy. If right after the plus in the expression we put a question mark, that's actually a specific directive to the regular expression code to say, stop being so greedy. And by doing this, we can then extract 3 distinct sentences. Okay? So that is the greediness problem. And the greediness problem most often comes up in examples where we have delimiters at each end of a match, kind of bookended matches, and then we have stuff in between, which could be anything that we need to capture. And so this is a recurring theme. Sat794 says, why then do you use the dot before the plus sign? The dot means match any single character, anything. The plus sign means match one or more of the prior character. So dot plus means match one or more of anything. Okay? So the dot is really just a wildcard saying, I want to match any character in that middle part. That's why I'm using it. Another aspect of regular expressions are what we call anchors or assertions. If in our pattern definition, at the beginning of the pattern, we use a caret symbol, that is an assertion that the following characters in the pattern definition must only match at the beginning of the data or the string being processed. If we use a $sign at the end of the pattern definition, that is an assertion that the preceding characters in the pattern definition must match at the end of the string being processed. Now, be a little careful here, because that caret symbol has 2 meanings. When you use that caret symbol inside of square brackets, that is negating a character set. When you use it outside of square brackets at the beginning of a pattern definition, that's an assertion that says we've got to match this pattern at the beginning of the string. Finally, in the regular expression PCRE world, there is something called regular expression behavior modifiers. The following expressions, when they're included in a pattern definition, will change the behavior of the regular expression engine, the pattern matching process, in the way mandated on this screen. If we put into the beginning of the pattern somewhere, parentheses, question mark I, close the parenthesis or close the bracket, that will disable case sensitivity. So that means ignore case. If we put question mark M inside of parentheses or round brackets inside of our pattern, that means match beyond the end of a line in a string. It is the meaning is M for multi-line match. So I didn't mention this earlier, but regular expressions tend to be line orientated unless you explicitly tell the engine to go beyond the end of a line. And then finally, question mark S as a modifier is something that tells the regular expression engine that the wildcard character, which is the dot, will also match line breaks. So we call this dot all. All right, a little bit more fundamentals before we get to some examples. And I know this is a lot of theory up front, but we'll get there to the examples in just a minute. The regular expression language also has the concept of a logical OR. If you use parentheses and a pipe symbol in a regular expression pattern definition, this forms a logical OR statement in the regular expression. Now, if we use this concept and combine it with custom sets, it actually allows us to refine our pattern matching to be highly specific. Let's look at an example. Match, here's the problem statement. Match the number of months, match the months of the year between 01 and 12. That is, we're trying to match the text 01, 02, 03, 04, 05, 06, 07, 08, 09, 10, 11, and 12. Okay. Well, we can use a logical OR to do this. And the way that it breaks down is inside the parentheses, we start off with the first match, which is the exact character 0, followed by a range of characters 1 through 9. That part of the expression will capture the 01, 02, 03, 04, 05, 06, 07, 08, 09 use cases. Then we have the OR symbol in the middle, and then on the right-hand side of the expression, we have the second set of use cases, and that is a character 1 followed by 0 through 2. So 10, 11, 12. And so by using this logical OR construct with character sets, we have sharpened or refined our matching down to very specific sequence of 2 characters. Okay. Now there's another concept wrapped in here, and that is this red question mark colon in front of the, well, expression, or if you like, right behind that first open parentheses. When we use logical ORs, we have to use parentheses, but the act of using the parentheses also defines something that's called a capturing group. And the characters question mark colon right after that open parentheses, well, they disable the capturing group behavior, rendering only a logical OR in the pattern we're defining. Now, right now, that means nothing to you because you don't really know what a capturing group is. But on the next slide, we're going to talk about what a capturing group is, and it will make a little bit more sense. And then when we get into the examples, hopefully it makes a lot more sense. Capturing groups allow us to subgroup a part of this expression, also known as a sub-expression. When a regular expression engine, or the code, the C library, if you like, receives an expression with parentheses in it and processes that expression, the results get inserted into what's called numbered subgroups. and you can access the numbered subgroup, well, specific to the programming language or the context of use. Most often you see this in software programming languages because it's easier to express, let's say a Python expression, for example, to access a numbered subgroup in a programming language. But not exclusively. Sometimes you see people do this in grep and sed and awk and so forth, right? So here's an expression. This expression is what I would call a naive regular expression to match an IPv4 address. So if you look at this, it breaks down by octets of the v4 address. We're saying match \d curly brace 1, 3, and then we're subgrouping that match, and then we're putting a dot between each octet group. And because we explicitly have to match a dot, not use a wildcard, we escape it with the \. Now, because we've also used these parentheses inside the expression, we now have 4 subgroups in this regular expression. In red, that's group 1, in green, group 2, in blue, that's group 3, and then in a brown color, that would be group 4 as part of that match. So that is the concept of capturing groups. Now, you don't have to use capturing groups to match an IPv4 address. I could eliminate the parentheses from this and just do an entire single match on an IPv4 address, and it would work just fine. There are some special circumstances with the regular expressions that we need to accommodate, some of which I've already talked about. We already know, for example, that the dot character is special. It's a wildcard. It means match any single character, right? We know that the left square bracket and the right square bracket in a regular expression is a special character, because that means to define a set. We know that the open parentheses and the closed parentheses, or round bracket if you like, that means to define a capturing subgroup or to contain a logical OR. But what if you needed to match in the text an actual left bracket? Or what if you need to match in the text an actual period or a dot? Well, these are special characters, right? They have meaning. We can do something called escaping to accommodate this situation. For example, the expression square bracket A to Z, close square bracket, \W plus dot matches one uppercase letter, one or more word characters, and then any single character. If we put a \, in front of the dot in that expression, it changes the meaning of the expression. It again matches one uppercase letter, one or more word characters, but then exactly matches a single period or full stop, because we escaped the meaning of that dot. It no longer means wildcard. It means, no, I want you to match exactly a dot. Okay? And so those special circumstances sometimes apply for us. I feel like I've covered a lot of theory and not a lot of examples. So let's do a screen here of some examples of regular expressions, right? And so on the left-hand side, we have the data that we're matching here. Sorry, let me try that again. On the left-hand side, we have the regular expression definition, right? That's our pattern definition. On the right-hand side, we have the string that we're going to try and match against, right? So if the regular expression pattern was defined just as the word hello, H-E-L-L-O, that's what we call an exact match. It will scan Pac-Man, if you like, right? Will start to consume that string contains the string hello until it finds an exact match for the letters HELLO. And it will extract one match in this case. Okay? So that's the simplest kind of example. The second example, let's match using a logical OR the word gray or the word gray, changing the spelling in the second case to have EY instead of AY in the spelling of gray, right? Now, when the regular expression matches, it will match anything in that string that has the spelling as GRAY or GREY. It will match only 4 characters of either of those words as that regular expression is defined. Now, that's not the only way to define that regular expression. The only thing that differs in those 2 words is the A or the E in the spelling, so we could define the same expression with the exact letters GR, open parentheses, question mark, colon, to disable capturing group behavior, A, pipe symbol, E, close the parentheses, and then the Y on the end. That means match GR followed by either the letter A or E followed by the letter Y. Okay? So that expression works in the same way, that third one down. All right, here's one that's good for us in the information security community. What if we wanted to match hexadecimal characters? Well, this is a really good expression. Now, the form is it has a 0x in front of it, and then it can be 1 or more hexadecimal digits. So we can put in the expression 0 followed by an X, and then define a custom set. And the custom set is only going to be the legal hexadecimal characters. And we're going to accommodate uppercase and lowercase. So we put 3 different ranges into this custom set. A through F uppercase, A through F lowercase, 0 through 9, and then a plus symbol after the custom set, meaning match 1 or more of the previous character. Now you need to understand here that in this example, that custom set we have defined matches only a single character. The plus symbol after the custom set means match 1 or more of this single custom set character, which is in this case 1 or more hexadecimal digits. Okay. \D plus, a simpler example, match 1 or more digits. Okay. 1 or more digits, \D is a predefined set. \D curly brace 3, close curly brace. You've got this by now. Match exactly 3 digits. What about this one? \W curly brace 2, comma, close curly brace. Match 2 or more word characters, where word characters are defined as the predefined set, A through Z uppercase, A through Z lowercase, 0 through 9, and the underscore. All right. Jumping to the last 2 examples, because you've already seen a phone number, caret symbol and then the letters dog, D-O-G. That means match data that only begins with the word dog. So we're using an assertion here. And then the very last example, match only data that ends with the word jumps, plural, and it has to have a period or a full stop on the end. And then the dollar is an assertion, meaning match only that data at the end of the data that we are processing. So if it has something like jumps in the middle, it won't actually match that in the middle of the data. Okay. I think it's time for a break. So let's take a 10-minute break. I'm going to bring my timer back up on the screen, and let's get ourselves a stretch, a rest, maybe a food or favorite beverage, and we'll resume in exactly 10 minutes. Hello, folks. Sorry for the little delay. I had a landscaper show up and I had to talk to him a little bit about a project that is occurring in my on my property right now. So trying to juggle too many things. Anyway, let's keep going. Sat794 says, could you please go back to the sentence matching example? You did not show how separate sentences can be created from the paragraph without the dots in between each word. I think you misunderstood. Well, no, you're right, actually. Why don't we do that with an example? And let's just pull up a web browser, okay? And let's go to regex 101, which is one of my favorite sites for testing regular expressions. All right. And we're going to do a bit of live off-roading with regular expressions. So I think we'll type in the data. This is a sentence to be tested. And I think what you're referring to is, how do we actually match words, right? So \W plus is one way to match words right now, and we do have multiple matches here, right, for \W plus. So already, just by doing that, just because of the definition of \W, we have a separator. However, if we wanted to be more explicit and use the border character between a couple of words, we could actually use \B in a more explicit fashion, right? Now, let's see. I'm going to be very explicit here. Let's see if we can get a match. I probably should select PCRE. We are PCRE right now. So, let's see, \W plus. And then we can probably subgroup that. So here we're subgrouping, we're creating one word, we're doing a \B, and then we got another \W plus. I can't do this like live off-roading right now, but anyway, \W is the idea for separating words. It's going to be a little hard to live off-road that. So hopefully that makes a little bit more sense for you. Let's go on to an example we can really get our hands around that's a little bit more complex, and that would be matching a credit card number. Okay, so if we think about for a minute credit cards, to match a credit card number is an ideal job for regular expressions. But it turns out that it's not a naive thing to do if we wanted to get more of an exact match. For example, we have very specific rules around different card vendors that apply here. Visa cards start with the number 4 and they have 16 digits total. Now, some older Visa cards only have 13 digits. MasterCard numbers have even more specific rules. They start with the numbers 51 through 55, or with the numbers 2221 all the way up through 2720, and they have 16 digits. American Express numbers start with 34 or 37, and they only have 15 digits. Diners Club, something that you don't often see here in the States, but it is outside the US. I know in Australia we see that a lot. Diners Club numbers start with 36, 38, or 300 through 305 and have 14 digits. All right, so you can see there's lots of rules here that we need to adhere to in order to do a credit card number match. In addition to not only the textual data matching that we need to do with credit card numbers, we have a checksumming algorithm that also applies in the context of credit cards, and that's called the LUN algorithm. It's a modulus 10 checksum algorithm. Now, because regular expressions are not a programming language, we cannot implement a checksumming algorithm using a regular expression. That's just not possible. We can implement it in some other programming language, and I'll give you a free Loon algorithm in Python in just a minute, just for fun and games. All right. Here's an example regular expression for a Visa card match. All right. So the rules around a Visa card, as per the prior slide, is they start with the number 4 and they have 16 digits total. However, some Visa card numbers are only 13 digits long. Okay, so we're using an assertion here. We're starting with the exact digit 4, and then we are following by exactly 12 digits. So in purple, that accounts for the first 13 digits. Okay. Then the second part of the expression, we have exactly 3 more digits, and these are a range of characters between 0 and 9. We could have used \d as well. In that last part of the expression, though, this match is optional, and so what we're doing is surrounding that green part of the expression with parentheses to put it inside of a group, and then we're disabling the capturing group behavior and then making that entire sequence of 3 digits optional with a question mark after it, right? So that means that the 3 digits at the end of the card number are optional, okay? Hopefully that makes a little sense for you. Now let's go to a much more complicated example, and that is a MasterCard, all right? So the first thing to understand about the MasterCard is, if we go back to the original screen, they all have 16 digits. However, the starting characters in the case of a MasterCard are a little bit different. And we have essentially 2 use cases here. We have the digits 51 all the way up through 55, and then 2 additional digits, or we have 2221 all the way up to 720 as that second use case. And so as we construct the regular expression, we need to separate out these use cases to account for the first 4 characters, and then at the very end, just match another 12 digits. Because of the first 4 characters is where we have some of this unique prefix activity, all right? So to reiterate, in purple, this part of the expression is matching exactly the digit 5, followed by the digits 1 through 5, exactly 1 of those, and then followed by any digit and exactly 2 of those. That gives us, starting with 51 up to 55 and then 2 digits, right? Remember, this is textual matching. We're not matching a range of numbers, we're matching a range of characters. The second use case is this start with 2221 all the way up to 2720. Now we have to break this down into a series of logical OR matches in order to get a handle on this part of the use case, which is these 4 digits. The first part of that would be the digits 222, 1 through 9. So that's right here, 222, and then the single digit 1 through 9. The second part, 223, all the way up to 239, okay, 2299, sorry. So that captures, for example, this part of the expression would capture 2230, 2231, 2232, all the way up to 2290, 2291, 2292, etc. And then we have to continue that logic out until we accommodate all of the possible variations to get us all the way up to 2720, right? And in the very last case, 2720 being the upper end of the range has to be an exact match. All right, so non-trivial, right? The way we have to construct this. And the reason that it's non-trivial is that we need to construct an expression that is matching characters in the string. We're not looking at number ranges, we're looking at characters and character ranges. And so we have to be very specific in our use cases to process that text in terms of the individual characters. Finally, a point on the Lun modulus 10 algorithm. This algorithm is protection against accidental errors in data entry. And the validation recipe of Lun, and this is just a bit of bonus material here for you, is written as follows. You double the value of every second digit from the right of the number. If the doubled value is greater than 9, you sum up the individual digits of the answer instead of using the actual double digit. For example, if it comes up to 18, then the value becomes 1 plus 8 equals 9, right? Then you sum up all the values of every second digit from the right and all the remaining digits in the odd positions. And if the result modulus 10 is 0, the number is valid. Okay, so this is a simple mathematical algorithm to determine whether a credit card number is valid or not. Because I went down this little tangent, I went out and searched for a Lun algorithm in Python. I found a couple of examples that I was not happy with. They were not efficient implementations. So I thought, hey, why not just put a slide into the class material that gives you an efficient checksumming algorithm for the credit card number in Python. And then you can, with your Python interpreters, use that wherever you like to use it. So there's a function in Python that implements the Lun algorithm for you and returns a 0 if it is correct. It returns non-zero if it is incorrect. All right. Let's roll up our sleeves and go a little bit further. Okay. What if in regular expressions we wanted to match an IPv4 address? There are two ways to think about this. We could write an expression which I would say is quick, dirty, naive, and prone to false positives, or we can write an expression that is very specific, precise, and exactly correct. Now, let's say you're going through some data in a log file and you're just pulling out IP addresses. Well, sometimes quick and dirty is a good enough expression. Here's an example of matching an IPv4 address in a slightly different way than the earlier example that you saw. I define a character set, and in that character set, I include a digit, which is \D, and then I include the dot, which is just the delimiter between the octets in the IP address. And then I say, you can match between 7 and 15 of this prior character set. What does that mean? Well, think about this sort of out aloud with me, if you like. The shortest possible IP address in terms of textual length is 7 characters. Think about 1.1.1.1 or 0.0.0.0. Well, what that is 4 digits and 3 dots. And so the number of characters there is exactly 7. The longest in the textual string sense IP address is going to be something like 123.123.123.123. In that IP address example, there are 12 digits and there are 3 dots, giving us a total of 15 characters. And so this quick and dirty expression is going to match an IPv4 address, okay? But it will match also invalid IPv4 addresses. 999.888.777.666, for example, is not a valid IPv4 address. However, quick and dirty is sometimes good enough, right? Sometimes we don't need an exact match, okay? Okay, now let's get paranoid. Let's say, look, I really need an exact IPv4 address match. I want to zoom in on this thing and get it exactly right. Or how would we break that down? The easiest way to look at this is to build an expression to match a single octet of an IPv4 address. Now, what is a single octet? Well, it is the digits 0 all the way up through 255. They are the legal digits in a single octet of an IPv4 address. Now, we must think in string terms, textual terms, as we're writing this expression. So we need to break this down by use cases again. Now, we know that the octet is either going to be 3 characters long, 2 characters long, or a single character long. We can start off with the 3 characters and build the use cases for the 3 character long piece, okay? Well, one of the use cases there is, let's match the digits between 250 all the way up to 255. And that's nice because, well, there's an upper bound limit, right? We only need a 5 as a second digit, and there is only 0 through 5 as the third digit. So it makes a nice separate use case. So we can, in our expression, we can say match exactly the digits 25, followed by a single digit in the range 0 through 5. And that will match 250, 251, 252, 253, 254, and 255. That's one use case taken care of. Now, in the red color here, let's think about the second use case. And the second use case is with considering, again, 3 digits, can I match the numbers that all start with a 2 but go up to 249? Okay, so now the only variation is the second and the third character in the octet. And yes, you can, because you can think about that. The second character is going to have a 0, 1, 2, 3, or a 4. The third character is going to have a 0 all the way up through 9, and the first character is always going to be a 2. So we can define that with our descriptive regular expression language by saying the exact character 2 followed by a digit in the range of 0 through 4, followed by another digit in the range of 0 through 9. And that gives us 200, 201, 202, 203, 210, 211, 212, etc., all the way up to 249. Exactly. Right? The third part of the use case here is the rest of the digits. How am I going to match a 0 all the way up through 199? Now, we could have divided this into 2 different use cases if we wanted to. We could have decided, hey, let's match everything that is 1 digit, then maybe 2 digits, and then the remaining 3 digits between 100 and 199. But it turns out we have enough flexibility in the regular expression engine to do it all in one part of the expression if we use some optional matching. So a question mark after a character means match this 0 or 1 time, right? Let's pretend that the first 2 digits didn't match. This is a 0 or a 1 optionally. And let's just look at the second part here. The second part, we're saying the digits 0 through 9, followed by also the digits 0 through 9 with a question mark. If you think in your head, if you picture that, you will match 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you could match 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, followed by 1, 0, 1, 1, 1, 2, 1, 3, all the way up to 9, 0, 9, 1, 9, 2, 9, 3 to 99. If a third digit's involved, well, we want it to be a 0 or a 1 in front of that, which would give us the 100, 101, 102, 103, 104, etc. Okay? Now, why would I do it this way? Well, it is possible for people to express an octet in an IPv4 address with three digits that have preceding zeros. For example, they could write 001 or 01, right? Even though it's not typically seen, it is legal, and we would want to match that use case. And so we have enough flexibility in this expression to match that particular use case. And there we have it. Now we have a complete expression with some optional matching in it. We have disabled capturing group behavior for a single octet of an IPv4 address. The only job left for us now is to put 4 of these things together, because we are dealing with 4 octets, not a single octet. And so to do this, we can put a \dot between each individual group. Then we can group that up and say there are 3 of them, and then exactly 1 octet on the end. And then we have a total of 4 octets. Woo, man. So you're probably thinking to yourself now, regular expressions to do a relatively simple task of matching an IPv4 address can get pretty complicated. And the answer is yes, they can. But if you understand the language definition of a pattern and you break it down in your head as you're reading the expression, you will be able to interpret the expression. I also highly recommend that if you're documenting a regular expression in, let's say, a wiki or on a Git repo as a markdown file, that you break it down in the documentation specifically. You point out the different features, and if you're doing it inside of software, then put comments in your code that break it down for the person that comes along and has to look at it, because they need to know what that expression does. All right, switching gears just for a minute. Let's go to Linux and Unix regular expression support. So we're switching gears over towards a mixture of POSIX and PCRE. The grep tool in Linux or Unix, by information security professionals, I would say is one of the most often used tool in the Unix operating system. We are using grep all the time. The problem we have in the industry is we are not using grep as effectively as we could, because grep fully supports basic regular expressions, extended regular expressions in POSIX, as well as supporting PCRE compatible regular expressions in the full GNU version of grep, later versions of grep. Pretty much stuff you will see on Debian-based Linux and Kali, etc. So we should probably learn how to leverage the full power of grep with regular expressions, because then our grep foo gets much, much stronger. Sed is another tool that we use a lot. This is the stream editor. Sed only supports extended regular expressions, EREs. These are POSIX-based by definition. The awk tool, another commonly used tool in the Unix operating system, the initials, if you cared, stand for Aho, Weinberger, and Kernighan. That's how awk came about. With logs under Linux, by the way, you can produce lots of excellent geek foo, as I like to call it, just with the commands cat, tail, cut, less, more, grep, sed, tr, awk, sort, unique. There's a lot of stuff we can do that gets us really good results. Back to awk for a minute. Awk supports both POSIX-based regular expressions as well as PCRE-based regular expressions. Our favorite text editor, VI, or Vim, some people would say, but that really is something that stands for VI improved. I will forever call it VI because that's the generation I grew up in. I'll just say it that way, okay? VI improved supports its own flavor of regular expressions for search and replace, which are effectively based on sed. And you've got to think about this in the context of history. Sed postdated ed, and VI postdated sed. So the sequence goes ed, sed, VI, right? Ed is the initial command line editor, sed is the stream command line editor, and then VI is the full screen editor, and they all have a history. They grew up together in the Unix operating system. All right, let's talk about awk. So awk is a domain-specific language for text processing. It's typically used as a data extraction and reporting tool. Wow, sound familiar? It is a standard feature of most Unix-like operating systems. Now, in my case, I kind of missed the boat on awk because, well, I got kind of bogged down in Perl, right? I sort of ignored awk in favor of Perl, and Perl wasn't inspired by awk, and, you know, frankly, that became the downfall of humanity. I'm really kidding, but part of me is not kidding because Perl was a little painful. Now, awk is an interesting and powerful tool by itself for line-by-line text processing applications. Awk understands regular expressions, ERE, POSIX-based, as well as PCRE. Let's look at a couple of examples so that we can understand how to do this in awk. With awk, the things between forward slashes become the pattern that is to be matched. Capture groups are possible with awk if we use the built-in match function, and substitution can be done with awk, regular expression-based substitution, if we use the gsub function. Now, awk's syntax tends to be essentially match, then action statement. So in the first example, we are using awk to specify a regular expression, and the expression is dot plus bash dollar, and then the action statement in the curly braces is print $0, and print $0 will be the resulting match from the regular expression, and then apply all of this to the /etc/password file. And because you now have enough regular expressions rattling around in your head, you can already tell that this awk expression looks for all of the lines with users that are using the bash shell in the etc password file. Notice how the dollar assertion is there, saying that the line in the etc password file must end with bash. So if the user had a middle name of bashful or something, it wouldn't match that, right? The second example is an awk example that performs regular expression-based substitution. So we're using the awk gsub function to search for the text root and replace it with the text Toto. Now, any regular expression must always have forward slashes around it in the case of awk. And again, we're processing the Etsy password file here. And so you would get on the screen all of the words root replaced with Toto, right? The third example, we are going to use a capturing group, and we are matching using $0, and $0 essentially is the standard input coming into the awk utility when you use it in a function like this. We are matching with the expression caret subgrouping \w plus colon dot plus bash dollar. So we are finding specifically all of the users, because the user field starts at the beginning of the line in the Etsy password file that are using the bash shell. And to get the result of the subgroup match, we use print a square bracket 1. And a square bracket 1, well, a is kind of like a variable where the results end up. Square bracket 1 means give me subgroup 1 that matched, and that will be the user themselves. Okay. Proxmark says grep command not found. Well, if you type grep in uppercase on a Unix system, it will not be found. Unix commands are always lowercase, and that is the way the world should be. The world will literally spin backwards if you try to use uppercase in Unix commands. It is an abomination to the world that we know and love. And that's all I'm going to say about that. Let's look at grep. Grep, with Perl compatible regular expressions, could be used to detect, well, UDP traceroute activity in an IP tables log. So this is literally my perimeter firewall. I jumped on the box, I tailed my IP tables log, and then used grep with a Perl compatible regular expression to match any packets specifically with a TTL that contained a single digit, so that is a low TTL by default, with a protocol of UDP and a destination port of 33434, which by definition is the very first port number that the traceroute tool uses to solicit the ICMP port unreachable messages back from individual router hops as it traces through a network. And so I get results nicely highlighted in color that show me these low TTL packets as people have been probing my network with traceroute commands externally. So that was one example that I could think of when I was sitting here looking at grep and looking at Perl compatible regular expressions. But then I thought to myself, you know, there is a much nicer example that I could show you. And that example would be extracting URLs out of web content. But to do this, we need some advanced features in the regular expression. Now, one of the unfortunate complications is that regular expressions does not support back referencing with traditional capture groups. However, regular expressions does support the notion of back referencing with a feature called look ahead and look behind. Now, why am I saying this? Well, we need to look ahead and look behind with regular expressions when we are trying to perform delimited matches. So let's imagine a scenario where we have the HTML content of a web page coming back to us on the command line. So we're just going to use the curl tool in Unix, which is a very useful tool for just fetching the content of a web page. But then we're going to pipe the output of curl to a grep command, and we're going to make it case insensitive, use a PCRE-based regular expression, use color to highlight the results, and then specifically construct a very carefully constructed expression to extract exactly web URLs out of the HTML content. So let's go to the next slide and break down that expression, okay? By the way, I just remembered, I didn't tell you, but in that zip file that I uploaded to the resources channel, there is a PDF of the content of the show here so that you do have a copy of the slides. Look for that. Hopefully it's there. I think it is there. If you don't find it, let me know and I will make sure that I take another look. So what does the grep content look like then? Well, let's break down the actual expression. First of all, uppercase P means use Perl compatible regular expressions for this grep command line. Lowercase o means show only the non-empty parts of the lines that match. So we only want to see the data that actually matches, is what that means. Now here's what the regular expression looks like. First of all, $I in parentheses disables case sensitivity. That means ignore case. This portion of the expression in the first set of parentheses after that is the look behind portion of the expression that is denoted by this ? less than equals. Now this is specific to grep, and it is saying look for a delimiter of the text href equals with either a single or a double quote in a set there. Now we had to escape the double quote because there is a double quote surrounding the entire expression, and we didn't want the bash command line to inadvertently terminate early. Now in the middle part is our expression to match a URL specifically. And that would be exactly the text, HTTP S ? The question mark in a regular expression pattern right after any character means the prior character is optional. So this will match either plain text HTTP or TLS-based HTTPS. Then we match exactly : followed by another set. And the set here is anything that is not a single or a double quote, one or more of them. In other words, anything that does not delimit the end of that URL, that's the stuff in the middle. And then finally, we have the look ahead, looking for the single quote or the double quote to delimit the end of the URL. And there's our whole expression. And when we do that, just like you saw on the last slide, we get this beautiful list of URLs out of any web content. Now, I don't know about you, but I think that is an incredibly useful expression. I can go to any web page and I can pull out all of the URLs. I could even use maybe some recursive fetching of web pages in curl and pull out URLs recursively and sort them. So there's a lot we can do with this. That's a really, I think, great gift and a very useful expression for you. Let's talk about sed. Sed, the stream editor. Okay, Well, what is SED all about? Really, SED is about using the Unix pipe mechanism to process lines of data and apply some sort of expression to that data. And it's very common to use a replacement of text in a SED expression. If you use uppercase E as the parameter to SED, you can express a POSIX ERE expression with SED. And if you separate the expressions by a semicolon, you can even express multiple SED expressions. So the task I put in front of me was, okay, you have a file of data, that's text data. The file contains names. The names, well, let's just say the data entry was poor. The names have additional spaces between them. Some of the names have additional spaces on the end. There is some of the names with preceding spaces in front of them. Can we write a SED expression to process the data and get rid of the prefix spaces and the ones in the middle, substituting back for one, or spaces at the end, and so on? So I divided my SED expression into three subcomponents. The first expression is a regular expression, and in the case of SED, we need slashes. This means search for data that begins with a space and one or more of them, replace it with nothing. So just two slashes together, there's no characters in between. So that gets all of the leading spaces in a name. So for example, this one where there's two spaces in front of Joff, that part of the expression would eliminate those two spaces. The second part of the expression here, another SED expression, substitute one or more spaces at the end of the line with no spaces, with nothing. And that would get any of these trailing spaces back here. Now I've used asterisks. I basically turned on a VI option to show spaces that are trailing with asterisks so that we could see them there. And so that gets me the trailing spaces. The last part of the expression is, and it will, by the way, process these in sequential order, is search for anything that is more than one space and just replace it with a single space. And that gets the spaces that are in between the names here. And so when we do this, we cap the file, which displays it to screen normally. We pipe it through this big SED expression, and it cleans up the data for us, getting rid of those leading spaces, trailing spaces, and any additional spaces in between the first and the last name. So that's one relatively simple example of using POSIX-based regular expressions with SED. Now VI, or Vim, well, Vim is rather special. All together now, we love VI. We love VI. We really love VI. And we do love VI because Emacs is a standalone operating system. And if you're using Emacs, I strongly recommend you move away from it. But I do have strong opinions. Okay? VI is your friend, but VI has a more difficult learning curve. VI is split between what's called editing mode and command mode. In command mode, we can use regular expressions to search for and substitute data, just like we did with SED on the command line. In the case of VI, that expression can include a range of lines in the expression. So in this first example, I'm in command mode by typing escape and then colon, and then dot comma dot plus 2 means for the first 2 lines from the cursor position, substitute a single space with a hash symbol. And then do it globally, meaning if there's more than one of these on the line, go ahead and do it for the entire line. All right, my cursor was sitting right here. So at line number 1, and then 1 plus 2, bringing me up to 3, apply this expression. And so the first 3 lines, I get these pounds or hashes being put in there, matching my expression. All right. Now you can also do it this way. 1, 4, search for a single space replaced with a hash or a pound, use the global option. Therefore, we get from lines all the way up to 4, 1, 2, 3, 4, all of that material replaced. There was a trailing one in there still from the first expression, I think. Anyway, that's a bit of how VI might work with regular expressions and substitution-based regular expressions. All right. JavaScript supports PCRE. All right, so if JavaScript supports PCRE, we really should not have input injection vulnerabilities in web apps, right? Yeah, sort of, right? Don't forget about output escaping and encoding, which is actually more important for sanitizing data in web apps to prevent things like cross-site scripting and other injection vulnerabilities. Absos 13M asks, does VI have memory issues with large files similar to VS Code? First of all, VS Code is a bloated piece of software. VS Code has a huge amount of functionality in it. Therefore, if you open up a large file in VS Code, it will have excessive memory consumption issues. VI, on the other hand, is not a bloated piece of code. If you open up a large file in VI, it will use much less memory, and it is much more efficient, and it will, in fact, be more likely to survive opening up large files. But memory is not inexhaustible. If you try to open up a 20 gigabyte file with VI and you have, let's say, 16 gig of RAM on your machine, of which the operating system's probably using 2 to 3, your system's going to crash. Okay, so memory is not an inexhaustible thing. And it's one of those things, you go to swap and people kind of forget that RAM, random access memory, is not inexhaustible, and the operating system can only deal with so much. So in JavaScript, we have things like exec, test, match, match all, search, replace, replace all. All of these things actually support regular expressions in JavaScript, right? So great. We should not have issues with our web developers and dealing with regular expressions in their code. Well, that's not really the case. There is a common issue, in fact, with JavaScript of what I would refer to, and many others refer to in CVEs and so forth, of something called catastrophic backtracking, otherwise known as a regular expression processing denial of service. It goes like this. If your regular expression in whatever programming language is not well optimized, then the combinations that are checked for a match can be essentially computationally owed to the order of n squared, right? Meaning you have an exponential computation processing power usage for the way that the regular expression is written. And this most often will happen with things that include things like stars and and plus quantifiers, right? It's an issue. So it can happen with any regular expression engine, but it is particularly damaging in the JavaScript context, because the JavaScript context is usually code that is processed in the browser by the JavaScript engine, inside of your web browser client or by Node.js, for example, on the server side. And if it does exist in JavaScript code, you can get into this situation of a catastrophic crash. And this is something that you may have seen. You've seen a web browser tab, for example, when you open it up, that under certain conditions will just crash. It will use up too much computation power, and then the watchdog process in the threads of the web browser will say, hey, this tab is not responding. Do you want to kill it? And that's probably because of something like a regular expression denial of service that's occurring. And in fact, there are JavaScript libraries out there that have CVEs on this topic. And that will continue to happen as long as there are developers out there that don't fully understand regular expressions or should I say, don't optimize their regular expressions well enough. All right. Having said this, it is time for another break because I have talked again for another hour. So let's go ahead and set ourselves a 10-minute timer and take a break, get a drink, get food, favorite beverage of choice, favorite snack, whatever suits you, and I will be back in 10 minutes. Okay, just coming towards the end of our break here. Yes, I saw a couple of comments in the Discord. I'll need to rewatch this a few times. Brain is a little mushy, coming together, so on. Great class. Appreciate all those comments. One of the things I like to do when I'm teaching is give you gifts, and the little zip file has some gifts in it. But I also like to pack in so much material that it gives you a little sort of post-event studying that you'll need to do. And that's really just me trying to give you good value for money. And in this case, this class is pretty inexpensive, so I think good value for money, I hope, is achieved. And it seems that some of your comments definitely are leaning that direction. All right. Here is an interesting slide. Did you know that Bash and ZSH and other shells actually support regular expressions? In the case of Bash, since 2004. Not many people actually know this. The support is POSIX rather than PCRE, but there is lots of examples of being able to use Bash and regular expressions together. Now, just to kind of reinforce this, I'll try to find a terminal window here and see if I can't show you some things. So you might have noticed, I'm going to throw a terminal window up on the screen here. Like I said, you might have noticed, come on, expand font, make bigger. Okay, it's not working. Hopefully that's big enough for everybody to see. That I gave you a zip file, and in the zip file, there is various files in there. And one of those is a Bash regular expression shell script. And in that regular expression shell script is several examples of Bash regular expressions just for fun. Additionally, in that file of goodies is a regular expression cheat sheet in both PDF and XLS format. PDF is just a PDF copy of that XLSX. So that is rather useful material. All right. So hold that thought for a minute, and I'll come back to it and demo the Bash regular expression examples. All right. So one thing to be aware of with Bash is it tends to be favor POSIX-based character classes in the regular expressions instead of PCRE-based character classes. And that's not terrible. You can either use POSIX-based classes in your Bash regular expressions, or you can use custom character sets as if they were PCRE. So either way actually works, right? So in the POSIX class case, well, if we wanted to match an alphabetic character, there is this concept of using square bracket colon alpha colon close square bracket to match an alphabetic character. If we wanted to match alphanumeric, there is square bracket colon ALNUM colon to match either digits or numbers. All right, and they've separated out some Unicode stuff here, but that doesn't really matter. And then there is square bracket colon punct colon to match some punctuation characters. So that's just a little bit of a difference with POSIX character classes, not enough to worry about. I normally will write more in PCRE style. In fact, I prefer to use custom character sets because they work either in POSIX or PCRE. So now let's look at the example, which is a Bash script with 4 different regular expressions in it. And there are 2 varieties of regular expression, one more PCRE style with character sets and one more POSIX style. And the first 2 are designed to match an email address, okay? And we all know the common format of an email address, and that is to the left-hand side of the @ symbol, you're usually going to have a sequence of characters or digits maybe a plus symbol, maybe a dash, maybe a dot, maybe an underscore, and you're going to have one or more of those. And so I defined a set which does exactly that. I defined a square bracket set here with A through Z lowercase, A through Z uppercase, 0 through 9, backslash plus, because plus is a special character. So I want to match actually a plus symbol, possibly in that set. Backslash dash, because dash has a special meaning inside of a set. It defines a range. So if we wanted to match a dash character in a set, we need to escape it. Backslash dot, because obviously dot has a special meaning, and then an underscore. So all of that's in my set, one or more of those, followed by the @ symbol, and then followed by something that looks like a domain name. And a domain name, the rules are going to be very similar, except domain name characters don't have underscores in them and they don't have pluses in them. They have all the rest of the stuff, so we just refined the set a little bit. In the second example, I used the POSIX character class of ALNUM, meaning alphanumeric. It's probably a little bit too wide of a set in some cases. Actually, no, it wouldn't be. It matches everything A through Z, uppercase, lowercase, as 0 through 9. So actually that does hit the mark. So it's just an alternative way of expressing the same thing, but putting a set within a set. Regular expression number 3 is the naive IPv4 matching expression. And you already saw this expression when I talked about naive IPv4 matching. And then regular expression number 4 is a highly precise expression to match a to match an IPv4 address. So how do we run this script? So this is my WSL system on my Windows box here. It is running Kali, and so that indeed has bash on it. We can look at the bash script and we can see that I've got all these expressions defined in the script, and then further down I'm actually using a little bit of logic in bash trying to match each expression and then echoing out whether it matches or does not match. So that's a little bit of advanced shell scripting there. But the important part is the equals tilde sign followed by the regular expression with no delimiters actually performs the regular expression match. $1 is the first parameter passed into the bash script. And so the intent is to try to match against anything you type in as a command line parameter, right? So I can run the script, type in joff@tld.com, and it will show me, even with pretty colors, that I matched the first 2 regular expressions. I did not match an IPv4 address. Well, that's actually not too surprising. Now I could type in 1.2.3.4, and I matched the last 2 expressions. One of them is a naive regular expression for an IPv4 address. The other one is a very precise regular expression for an IPv4 address. So now I could play that game where I type in 888.777.888.555 or something like that. And we will notice that the naive regular expression for an IPv4 address matches because, well, it's naive. It's kind of stupid, right? Whereas the precise expression for a IPv4 address does not match, which is what we would expect in testing our script. And so that's a gift for you, right? There it is, bash regular expressions. And so you can take that, adapt it, do whatever you want to do with it, and it gives you a sense of how to use those expressions inside of a bash script. All right. All right. And let's, before we get into a little bit of PowerShell, just pause a minute. All right. Any questions or concerns about the bash script or any other general regular expression questions or concerns? Having said that and pausing just a minute, it is my intent in this class to show you, to demonstrate clearly for you that regular expressions as a general concept apply in multiple contexts, in multiple languages, in multiple use cases. And I'm showing you various use cases to drive that point home, right? So having the skill, particularly of constructing PCRE-based regular expressions, is a really good skill to have. I'll just pause for a minute more. If there's any questions, I see Matt is typing right now. By the way, I do apologize. There is a slight delay between when I ask something of you and when I see the Discord results. And that's because GoToTraining itself is going to delay the video output a little bit. So Matt asks, how do you recommend practicing these? Your friend is regex101.com. So we'll show a programming language example at the end and how we leverage the regex101.com website to actually develop a Python script. All right. All right, continuing. PowerShell supports regular expressions straight out of the .NET framework base class libraries. There are several operators and commandlets in PowerShell that have regular expression support. The select string commandlet with -pattern, for example, has regular expression support. -match and -replace operators in PowerShell both have regular expression support. -split has regular expression support, and the switch statement in PowerShell with -regex also obviously supports regular expressions. Now, one variation with PowerShell is that PowerShell regular expressions are case insensitive by default. It's as if you put that parentheses ?i close parentheses, right? Now, on the commandlets, you can put in a -case sensitive option to change this. For the operators such as match and replace and split, you can use -csplit, cmatch, and creplace, and that will make those three operators be case sensitive. Specifically in the case of PowerShell, the regular expressions are using the system.text.regularexpressions.regex object directly out of .NET, meaning the regular expression support in PowerShell is going to match pretty much precisely what it looks like in the C# language or any other .NET language, because it's using the same base class object to implement the regular expression. So PowerShell is PCRE with some extensions. Some of the extensions date back to some of the historical Unicode support in the Windows operating system. For example, there is a \P curly brace is Cyrillic match, which is kind of interesting. If you want more detail on the regular expression reference from .NET perspective, you can go to the Microsoft website and look up the regular expression quick reference, and you will get exactly that. Let's look at some PowerShell examples. We can search for US-based Social Security numbers, for example, in file contents by using getChildItem -path, some sort of directory path specifier, pipe to select string -pattern, and construct a pattern that looks like a Social Security number, which is almost like a phone number. It's very close. \d \d \d. Social Security numbers are often delimited with dashes in them, and you would find files with Social Security numbers in their contents. Therefore, you have a very quick and dirty, in this case, data leakage protection or data leakage prevention kind of solution, right? Well, you would have to do the prevention part, but you get the idea, right? With the operator, well, you would most commonly use that operator in something like an if test. But on the command line, we can demonstrate it just by typing in an IP address string within the single quotes and then match it against a regular expression. In this case, we used our naive regular expression. Okay, dash replace. In the third example, I set up a variable containing the string, my credit card number is 1234-4321-9876-1212. Obviously, that is not my credit card number, but it is a example of 16 digits in credit card number format. I could say $M dash replace my regular expression in single quotes, which in this case is any 4 digits, right? \D, curly brace, 4, close curly brace, and replace it with the string XXXX. So I'm trying to redact, if you like, all of the digits in that credit card number, and you would get the output. My CC number is XXXX dash, and so on, right? So I'm just using a little bit of PowerShell. Now it gets even better in PowerShell, and this, I really like this feature. Commandlet parameters, if you're programming in PowerShell, allow you to validate that input parameter based on a regular expression pattern using the keyword validate pattern. Okay, so in that param syntax, we can put in square brackets, validate pattern, express our regular expression in between parentheses and single quotes, and then say, yeah, we're expecting a string and we want to put it in social security number. All right. And then when we use that commandlet, in this case, it's just called get data, and if the data we supply does not match the parameter, the validate statement in that parameter, we will get an exception, right? We will get a, hey, I cannot validate that parameter SSN. The argument Kevin does not match the \D, etc. pattern, right? Supply an argument that matches my pattern and try again. So that's a really, really nice feature, and validate pattern can actually be used even to validate ordinary variables. You can use it just as a standalone variable data validation mechanism. For example, I could type in square bracket validate pattern, open parentheses, \D, forward slash, \D, forward slash, \D, right? And that would attempt to validate effectively what looks like a date, which is a sequence of 3 sets of digits separated by a slash. Now, it wouldn't validate it very well because the date could be invalid, but nonetheless, it would do basic data validation on that variable. So that's pretty cool, right? And just to reinforce this concept, let me just double check on something here. If I move my cheat sheet to my desktop and then open it up, this means I'm going to have to drop out of the show really quickly. Okay. I want to just demonstrate and show you this PDF cheat sheet a little bit. Everything we're talking about today, I tried to capture into a single cheat sheet. And so those PowerShell things I just talked about, they're actually listed in a box on this cheat sheet. The Linux and Unix command line support I talked about are listed in the cheat sheet. The credit card examples are listed in this cheat sheet, right? Some Python functions, which we'll talk about in a moment, are also listed in this cheat sheet. And all of the basic construction of a regular expression pattern and all the rules around it, including the anchors, the assertions, the behavior modifiers, the greedy conversation, the quantifiers, etc., are all in this cheat sheet. So that is a very useful mechanism for you as a condensed version of everything we are talking about. And just so you know, Rivergum Security LLC, that is my company that I use just to support teaching and content development materials. So just in case you were wondering. All right. Okay, let's continue on. And I want to talk about a little bit of Python. All right. So at this point in the show, we have covered some regular expression syntax that looks at sed, awk, grep, vi, right? We have looked at regular expressions in PowerShell. We've looked at regular expressions in Bash. We've looked at regular expressions from a fairly neutral standpoint of just considering the expression itself. What I wanted to do for the remainder of the class, and it is more challenging, especially if you have no programming experience, is talk about regular expressions in the context of a programming language. And the easiest one to consider for that conversation, frankly, is Python, because Python is a highly intuitive language, and it is probably the easiest way to get on board. That does not mean that the concepts that I'm about to present in Python are trivial. They do take some studying, and you are going to be much better off if you have some programming experience. So please forgive me if you do not, but I felt like it was important to introduce some Python to put that programming context up with regular expressions. All right, so there's the disclaimer. Now, as I was writing these slides and finishing them out towards the end of 2020, and this was literally coincidental, I happened to look up on Twitter, and occasionally I tweet around the place, and there was a tweet right in front of me from none other than Guido van Rossum himself, whom I follow, and I think he follows me as well. And Guido van Rossum is the original author, leader of the Python project, dating back to late 1989, if I remember the details correctly. So Guido's an interesting character. Anyway, Guido decided, as he says here in the tweet, that retirement was boring, and he's joined the developer division at Microsoft. All right. Now, I went up and looked last time I taught, and I believe, and you guys can check me on this, that Guido is still at Microsoft. So what does it really mean? Well, make using Python better? Yeah, probably, right? Python 3 as a programming language and scripting language is pretty solid, but more integration with Windows is going to get interesting. And I think this will be in the Windows 11 and beyond space. And it's already showing evidence of that with the kinds of open source integrations that Microsoft has been reaching out to. So I think this was a fascinating tweet. Having said that, I digress slightly. Let's talk about regular expressions in Python. In the Python language, regular expressions are all contained in terms of the support in a module that is built into the language called RE. Now, RE is based on the Perl compatible regular expressions C programming language library. In fact, it's probably ported directly from that C programming language library if you really go look at the source code. Great. Now, one of the challenges with Python is that you can define a regular expression either to match against a byte object or a byte string or a UTF-8 encoded string. Now, why do I say that? Well, first of all, Python 2 is deprecated as of 2020, officially, mid-2020 to be precise. And so that going forward in our community and everywhere else, we should be focused on Python 3 if Python is of interest to us for producing some automation. Now, one of the major changes in Python 3 that really upset some people and tripped them up is the fact that Python 3 introduced string objects that are UTF-8 encoded instead of what were originally just byte-orientated strings in Python 2. In fact, Python 2 didn't really have a good concept of Unicode or UTF-8 encoding. It had some bolt-on stuff, but it wasn't done and integrated with the language. So that became a major change in Python that requires us to treat binary data and textual data separately and differently, effectively, okay? So having said that, as we go through this section, it'll become a little more clear what some of those issues are, and I'll talk about them. So let's start with a very simple Python example. On the screen, I am using the Python interpreter in interactive mode. That is to say, I literally got into a terminal window and typed in Python 3, and I drop into an interactive interpreter. And then I typed import RE to import the regular expression module. And then the simplest regular expression function to use in Python is something called find all, right? And so we could say find all, my regular expression is BHIS, and then the data I'm going to match against is I love BHIS, we all love BHIS, BHIS is cool. Col is cool, all right. And the find all function in the Python regular expression module actually returns back what's called a Python list. And that list contains all of the matches that successfully occurred. And we could assign this to a variable, for example, and look at the type of that variable, and we'll see that it's a list, right? And we could even get out list element 0 and list element 1, right? That's an example of a simple Python regular expression using find all. So when we're experimenting with Python and regular expressions, the find all function is the simplest way to perform that experimentation. Find all is, however, not the only Python regular expression method that we can use. Find all will find all occurrences of the pattern and return a Python list of results. There's a second and third function which are related to each other called match and search. Match will find occurrences of a regular expression pattern from the beginning of the data and return a special object called a regular expression object. It is not a list. And so you need to use another function on that object to extract the data, which I will get to. re.search does the same thing as match, but instead of finding occurrences of the regular expression pattern at the beginning of the data, it actually matches that pattern anywhere in the data that you supply. Now, with both re.match and re.search, we can extract subgroup matches. We get back, wow, brain fart there. Let me try that again. With both re.match and re.search, we get back a regular expression object. We can take that object and use a method called group to extract the specific matches from that regular expression object. This is not the same as re.findAll, which simply returns a list. re.findAll, another way to say that, is almost like instant gratification and very easy to experiment with in the interactive Python shell. All right, so let's look at some of that instant gratification, do some regular expressions really quick. All right, or maybe not so quick. re.findAll, \d is our regular expression. I can think of 5 great things about July 4th. I get a list back with a single digit in each of the matched entries. And there's the number 5 and the number 4 in that data. And so that makes sense. All right, re.findAll, \w plus. Find me something that matches the word character set, but one or more of them. In other words, find me all the words in this sentence. And we get a list of words in the sentence. I can think of 5 great things about July 4th as a big list. So there are multiple matches there. re.findAll, a single digit followed by a single word character. Well, Pac-Man starts consuming. Does an I match a digit? No. Does a space match a digit? No. Does a C match a digit? No. Consume, 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 consume. Does a 5 match a digit? Yes. But does a space character match a word character? No. Keep consuming until finally we satisfy the pattern with a 4 that matches a digit and a T that is in fact a word character, and we get 4T in the returned matched data. Making some sense, I hope. And I don't have to beat this ad infinitum, but you can see we kept on doing different examples to show how different expressions can match this same sentence. So the next one was \d, \w, which means a digit followed by 2 word characters. Well, 4th is the only thing that matches that expression. And so we get 4th in the result. Okay, \d followed by a space character. All right, I think you're getting the idea. How about this one? Caret \w plus, meaning match more than 1 word characters, 1 or more, only at the beginning of the data we're matching against. Well, the letter I is the only thing that satisfies that expression, because space is not a word character. So the 1 or more just terminates at the 1, and that's it. All right. All right, I won't beat this to death. I do want to point out something that nobody has asked me. Has anybody wondered why there is a lowercase letter r in front of the regular expression pattern string here? What is this thing? Can anybody answer that question? What does lowercase r mean in front of that regular expression pattern? Now, anybody who knows Python should be able to tell me. So Gunnar typed in, it means raw string. That is correct, sir. Now, the next corollary to that is, why would we use it? Right? Why would we use it? Right? Well, let's talk about Python string modifiers in general. Python string modifiers allow us to modify the behavior of Python strings. They're useful for the regular expression pattern definition to avoid escaping behavior or match byte string objects rather than UTF-8 string objects. What do I mean by that? Well, when we express \/ and a character in an ordinary string object inside of Python, and also many other languages, that sometimes can have a special meaning of its own. \n, for example, means line feed. \r means carriage return. We have an overlap here. We have a collision regular expressions also use backslash for specific character sets, like \W and \D. The collision is we don't want Python to reinterpret the backslash inside of that string to mean something else in the string. We want that backslash to be fed immediately into the regular expression engine, or the code that processes the regular expression, if you like. And to make Python do that, we tell Python, this is a raw string. And the raw string with that lowercase r means, hey, Python, do not reinterpret any of the backslashes in this string. Just send them straight on into that find all function. Don't try to interpret this as something else. Okay? That's what it means. So it's important. And in fact, in Python, when you're programming, and if you are using regular expressions, you will, I was about to say should, I'm going to say you will always put a lowercase r in front of the pattern definition, because if you don't, you will be a very sorry individual and a very confused individual. And just don't do that. Use that lowercase r, make it a raw string. Very, very important. Okay? Now, the other issue that can come up sometimes is the regular expression module in Python can work against regular expression string objects as well as byte objects or byte strings. And that's because in Python 3, we have two different types of data here, which we didn't used to have in Python 2. Everything was just a byte object in Python 2. Now we have UTF-8 encoded strings, and we have byte objects or byte strings. And byte strings are normally associated with binary data, right? If we want to use the regular expression engine against a byte object, we need to use a lowercase b as well as the lowercase r in the pattern, and the byte object in the second parameter has to obviously be a byte object. In this case, we artificially forced it by putting a lowercase b in front of that string definition of the IP address. Okay, so just an additional thing to bear in mind. All right. Python regular expression capture groups. Just like other implementations of regular expressions, Python implements capturing groups. Now, Python's implementation of capturing groups is very elegant, and I would say one of the best implementations of capturing groups that I've ever seen. Now, whenever you use capturing groups in Python, it makes the most sense to leverage the re.match or the re.search methods, because then you can take the resulting regular expression match object and use the group method with that to retrieve or extract the individual captured group data. Okay? And as a reminder, re.match and search, very similar. re.match is just not quite as computationally intensive because it searches for a pattern only from the start of the string object supplied rather than searching anywhere in the object. Here's an example. re.match, raw string, and then we have three groups in this definition. \D 4. That means, with the curly braces, exactly 4 digits. That's one subgroup. Slash, \D, bracket 2 bracket. That's another subgroup. Slash, \D, curly brace 2, curly brace. And then close those brackets, right? Close those parentheses. The idea of this expression is to match a date in the format year, month, day. YYYY, MMDD, right? And because I'm opinionated, I'll tell you that is the only way in our industry you should express a date, in my opinion. I cannot stand dates that are not sortable. And so year, month, day makes dates sortable. And by God, we should always do it that way, but nobody listens to me anyway. Okay. So if we try to match that against the data, I think 2021-03-17 is a cool date. Because re.match starts from the beginning of the string, it doesn't match that expression. It doesn't find it because the regular expression for the date, well, the date's not at the start of the string. And that's, a problem. Now, if I use re.search in that same expression, we do get a match. And we get a match on the 2021-03-17. All right. Now, once we get that match, what can we do with that? So let's perform the re.search again, but this time assign the result to another Python variable. So we'll say m equals re.search that date stuff. Now, using the group method in Python, we can extract the entire match if we don't supply a group number. So we just say m.group, open and close parentheses, and mind you, I'm doing this inside of the interactive shell, and there is an implied object print behavior in the interactive shell. So it just prints out whatever that function returned. And that function returned 2021-03-17, which is the entire match. However, if I type in m.group parentheses 1, close parentheses, I get the first subgroup that matched. And the first subgroup that matched is the year, 2021. And the same applies for then parameter 2 and 3. So the group numbers always count from 1. So that's how we extract in Python the subgroup matches or the sub-expression matches, right? Now, one of the other things I love, and I mean love, about Python is it has an enhancement for subgroup matching called named capture groups, or naming the capture groups. So numbering capture groups is all good and fine in expression, but it doesn't have any specific meaning. Python's module gives us extra syntax with $P less than a basic alphabetic name greater than to enable us to name the sub-expression or name the capture group. So we could use that same expression and use $P inside of the parentheses here, less than, year, greater than, and now that capture subgroup is called year, and the next one's called month, and the next one's called day. And then when we try to extract the data, we can either use the digit 1, 2, or 3 as a parameter to the group method, or we could use the actual named subgroup string to extract that data. And I love that. I mean, that just makes things just a lot more comfortable in terms of being able to use Python programmatically with intelligent regular expression construction, right? Now we can take this to the next level of capturing groups with Python by talking about back referencing. Do you remember with the grep example, I know it feels like years ago, but it was only about 30 minutes ago or so, right? We talked about this idea of look ahead and look behind. Python's regular expression implements what's called full back referencing in regular expressions, and this is a very useful feature for matching bookended or delimited data, just like the look ahead and look behind feature in the POSIX grep implementation. Now we can combine this idea with capture group naming as well. How does it work? Well, let's consider the same example in Python syntax, creating a regular expression to match a URL out of some content. Now, one thing I want to be clear to say is back referencing is way more powerful than look ahead and look behind. And the reason it is way more powerful is that the back reference at the tail end of the regular expression in this case understands to remember or back reference the same character that matched in the first group match. So if we're processing web page data and we encounter a URL that is delimited by a single quote here, it has to have a single quote on the other end to back reference in order for it to be a proper match. And this is the coolest thing ever, because we now have a way for the regular expression to remember what was first matched. And so that the delimiters are very discrete and well defined, and quotes are very common as a use case. So with that first expression, we used named back referencing. With the second example, we use just numbered back referencing, which just means that there is no capture group names. So \1 in the back reference portion in that brown color is referencing the first subgroup, is what that means. Really cool stuff, right? So what I find when I'm doing this, and we have a delimited match like this, is it is often best to use 3 subgroups. You certainly need it for the back referencing, but it sort of makes sense to put the stuff in the middle in a second subgroup, so it's all nice and discrete. So single or double quote, stuff in the middle, and then back reference the first delimiter. So we could implement the same concept that we implemented with our grep command inside of Python, where, if you remember correctly, I wrote a request which reached out to Reuters.com and, using regular expressions, extracted all of the URLs. We can construct a very similar regular expression using Python back referencing, and in this case, just in the Python interactive shell, I used the Python requests module to fetch the content from the web page and use the text attribute to get that content into a Python variable. And then I used re.findAll to match my regular expression against the content. And I ended up with a list of tuples in Python. Now, one other slight twist here is that if you use findAll with back referencing in Python, the back referenced part of the group match is not represented in the result. So each tuple here in the result only has the first match and then the stuff in the middle, and there's not a third entry there for that back referenced quote. And that's just the way it's implemented. That's fine. We don't really care as long as it works correctly with our regular expression. So taking this and putting it into a brief script, even though I typed that script in the interactive interpreter itself, here we are getting the content again, then we are looping through that content in Python, but we're looping through, in fact, the result of the findAll, assigning the quote and the URL to individual variables and just printing the URL. And we get exactly the same result in a small Python script as we used in our grep example. All right, so that's pretty cool stuff. Now, Python also has regular expression modifiers the same way as most regular expression engines. If you remember, I mentioned in PCRE there is the modifier $i for ignoring case, $m to make it match multiple lines, and $s, which is .all, meaning match new line as part of that wildcard match, which is more commonly used to match binary data, frankly. okay? In Python, there is a slight variation in that in all of the methods in Python, like find all, match, and search, that you can use with regular expressions, you can supply the modifier as a third argument rather than putting it into the actual regular expression itself, if you choose to do so. So re.ignore case is the same as putting parentheses question mark I inside of the beginning of the regular expression pattern, right? And you can see where I've used those two examples on this slide. Wow, I'm getting exhausted with all that. The very last section of class is quite complex. To sort of cap it off, it is going to be the development of a Python script, but I'd like to give you a brief break before we jump into that, so that everybody's well rested for the sprint to the end of today's materials. So let me reset the timer for a 10-minute break. Let everybody run out, get the beverage of choice, the snack of choice, and I will see you back here in exactly 10 minutes for the remainder of the class material. Okay, just coming back from break, and let's see if we can close this out. Okay, we're in the last hour of today, and I want to do a little bit of Python log analysis with you. Now, I warned you, and I will warn you again. This is a fairly sophisticated portion of the class, but the nice thing about this is I give you the code, right? I give you the tools to understand it better, and in time, I think you will find that this sequence is useful for you, and this particular example can be applied more generally to some of the tasks that you will encounter day to day. So it turns out that with a few Python programming tricks and the regular expression module, you can do some fairly sophisticated log file analysis. Obviously, helpful things to know is the fundamentals of a Python script itself, a little bit of file handling in Python, how to format and print data appropriately, how to leverage lists and dictionaries in Python, and then extending that, we're going to talk a little bit about the collections module in Python, which has a beautiful frequency counting dictionary, which becomes something that's extremely useful when you combine it with regular expressions. So this slide, just to give you a reference, is useful Python script outline. You've probably seen Python scripts online quite a lot, and you've probably seen some of the what might look like more unusual aspects of a Python script, such as the if name equals main stuff at the bottom, which can confuse some people. So let's just sort of walk through this. A normal Python script is probably going to have a shebang line at the top, and that's something that's mostly about the Linux and Unix shells, understanding that we need to use a different program to interpret the remaining contents of this file. That's what the shebang line means. Now, in an actual Python script, by convention, we always import modules at the top of the Python script. So that's right here. We're importing regular expression module, and we're also importing a module called argparse, which we're going to parse in the command line arguments. Then we have a function definition. Now, a function in Python is a repeatable block of code. In this case, the function we've defined simply is reading a file and printing the contents to screen. Further down in our script, we have a conditional test if _name _, that's called a dunder variable in Python, is equal to the string _main, M-A-I-N, then we'll execute these statements. And, you know, without getting too deep into it, that conditional test is simply a test in Python to see whether we are running this as a standalone script or we have imported this code into another script as if it were a module. If the name variable there is equal to main, we are running as a standalone script, which is what we will be doing in this particular case. Right, so I can't teach you all of Python today, but this is a basic script outline. I guess suffice it to say, the other thing to remember with Python is that it is an interpreted language, and the lines of code in a script like this will always get interpreted from the top to the bottom of the script. So if we're going to do some log file analysis, we need to be able to open a file. To open a file, we use the open method, which is a built-in Python function. You can specify a relative or a full file path as the first argument, and then you need to specify a file mode as the second argument. And the modes can be read, write, append, and so forth. If we are doing log file analysis, we need a mode of read. And furthermore, if we are doing log file analysis against text, which we probably will be, we need a qualifier of T, which specifies that we are opening the file in read and text mode. That implies, or that has the effect of returning all objects back to Python as we read the file
as UTF-8 encoded strings, versus if we opened in binary mode, it would return byte objects from the file instead of UTF-8 string objects. Now we can use an iterable against a file handle once we open it. FH was my variable I'm calling a file handle, to loop through the lines of text in the file. So this basic function is simply opening a file in read text mode, looping through all of the lines of text in the file and just printing them to screen. And then, because we're a good steward of resources, we are closing, the file once we finish looping through all of the contents. So I needed an example of something to process in this particular section of the course in order to give you a usable example, if you like, right? A useful example that we could apply both regular expressions as well as some of this dictionary counting stuff. And so I chose to use the Squid web proxy, and you know, in good faith and like I do a lot, I experiment on my family whenever I need to generate some log data. So I stood up a Squid web proxy, transparently redirected all of the web traffic to the proxy, and immediately started capturing data. Of course, my family didn't know that, but yeah, well, it's my network, so so be it, right? Anyway, the Squid web proxy produces a well-formed logging format, which has 10 columns separated by one or more spaces, and the definition of those columns are the Unix timestamp as UTC seconds and milliseconds, the duration in milliseconds of the request, the client source address, the resulting code, the bytes transacted, the request method, the URL requested, a user identifier, anonymous would just be a dash, a Squid caching hierarchy code, and that's not relevant if you're not using caching hierarchies, which I was not, and then the content type of the object seen in the HTTP reply header. Okay. So using this knowledge and using regular expression capture groups, we could name capture groups and divide out these rows of data, if you like, these lines of data into their individual fields of meaning and then process it. Okay, as long as we write an appropriate regular expression to capture that particular line of text. Okay, for example, for the first two fields, we could use a capturing group. We could name it timestamp, and we know that the definition of timestamp is a sequence of digits followed by a decimal point followed by 3 more digits, giving us the seconds and milliseconds from the Unix epoch. And we know this from not only reading the documentation, but we know this from looking at samples of data. Okay, so we could then start building out our regular expression. And honestly, the easiest way to build out a regular expression when you're passing through log data is just to paste some of the log data into the regex 101 website. You know, that's mostly running in JavaScript, so it's okay. I have an access.log here, which is some of this Squid log data. So I can copy and paste some of this over to the regex 101 website to use it as sample data to build out my regular expression. So let's do that, regex101.com. Let's take that tab over here, okay? And let's select Python as our regular expression language, because that's what we're going to be using. Paste some of that Squid log data over there, and then begin defining our regular expression. And I'm going to start with that timestamp, and then I'm going to say \d plus followed by \d3 and close the parentheses. And immediately you'll see that it starts to match. Now I know there's a space right after that, so I can put in a space right after that just to terminate that match nicely. And then I can look here on the right-hand side of the browser tab, and I can see my timestamp group named and matching, and I can even highlight it, right? And you can see the match. So this is a really nifty way of us starting to parse out that data in an appropriate fashion, right? All right, cool. So we can keep going, right? We had a duration, which was just digits, and we know it's always going to be \s plus between these fields, which is one or more spaces. So let's now define a group for duration. So we'll call that duration. All right, we are now truly in the twilight zone because we are off-roading and doing regular expressions live. Now we look at our match information. There's a duration match. We can highlight it. There's another duration match in the second line. Hey, I'm feeling pretty good about that. Let's try to go for IP address. So we'll call IP or client IP or something like that, right? And in this case, I'm going to be lazy and I'm going to use my naive regular expression for client IP, which is set \d\dot close set curly brace 7,15 close curly brace, and then do \s plus there. Now we have an IP address defined, right? So we're really off-roading it again. All right, there's our first one. There's our second one. And the beautiful thing about this is for every line of text we process, we have a clearly captured and named group for every field of data that we are parsing and separating out. It is really nice. I mean, just really nice, right? So we can keep going in that fashion and fully form our entire regular expression to properly pass out every single field of data in a line of that log text. And so once we have that expression, we can then embed it in our Python script, literally line for line what it is. I mean, it's a copy and paste. Now, one of the things that I have slightly modified in putting this regular expression in there is making sure it has the raw string qualifier in front of it. And then as I was defining the string object, I separated it out in multiple lines just so it's easy for us to read. And so I'm using line continuation and a plus symbol here to concatenate this into one big expression. But it is that expression completely defined and captured from regex 101. Then at the bottom of that regex definition in my function, I'm using another method in the regular expression module called compile, which is pre-compiling the regular expression to improve computational performance inside the loop as we process the data. Essentially, that prevents us from having to recompile it every single line of text that we're processing. We don't want to do that, right? So then we could extend our script a little bit more, and we could match with our pre-compiled expression the line of text that we're trying to parse through. And if there is no object returned, if not M, we just increment a failure count and continue. Otherwise, we increment a successful matches count, and then we go on through to the end of the file. So this is the very first iteration testing my expression in Python to see if it's working, okay? Now I want you to bear with me. I'm going to talk through a lot of stuff here, but there is a larger context in getting to the point of being able to process this data with Python and do something useful with the results of processing this data with Python. So right now, we have gotten to the point of being able to separate the data out into its individual component parts inside of our code. Great, that's a good start. Now, one quick tangent here. seconds dot milliseconds from the Unix epoch, which is January the 1st, 1970 at midnight, is not very human friendly and readable date. I don't know about you, but I cannot look at a number of seconds between now and January 1st, 1970 at midnight and say, oh my God, that is April 15th, 2010. I can't do that in my head, right? In Python, there is a date time module that has a particular function in it or method called date time, and date time can read in that seconds dot milliseconds value and reformat it as a human readable date time. And that's what I did here in this sample code. Very, very useful to be able to do that. So now we can extend our script inside this loop just a little bit more, right? By extracting out that date time field from the timestamp, and we have to cast it to a float here, a floating point number. That's a Python oddity because it comes back initially as a string. So we need to put it back to a float and then just print out some of the group data that I'm extracting, including a human readable date time, as well as the client IP address, as well as the URL. And then we can go back and validate and look to see if our script is working. And you just have to trust me right now, as I'm developing out this script, it is working. This is not my first rodeo with Python. In fact, I taught Python professionally for nearly 6 years. So yeah, trust me, this works, okay? The other thing you need to trust from me is that as I'm building this out in the lecture sequence, the completed result is available to you in the class materials as a SQUID log analyzer Python script. So you have the finished script. Okay. All right, so fabulous. We have the data we need. Now we can parse the log file itself and produce some goals or questions that we want to answer. Okay. For example, please create a list of URLs that each client IP address has communicated with. Or, what are the top 10 most frequent URLs seen in the proxy logs? To answer that question, either of these questions, we need some more power in our Python programming. There are 4 Python data structures that can significantly help us here. Dictionaries help categorize data. Lists are needed to list out items that belong to a particular category. The collections module has something called a frequency counting dictionary. So if we're looking for the most frequent URLs, that will be useful. And the collections module also has another useful dictionary called a default dictionary, which just makes the categorization logic a little bit easier. Let's talk about frequency counting briefly. The counter dictionary in the collections module has a way of performing automatic string counting, and to use it is really, really simple. To perform the counting, all that you need to do is supply a Python list of words to a counting dictionary method called update, and it will create a frequency count dictionary of each word and the number of times that word occurs in the corpus of text that you are analyzing. So in this code, again, in the interactive shell, I'm just defining a big paragraph of text. Then I am creating a counter dictionary, and then I'm updating the counter dictionary after splitting all of that text into one big list of words. And then I show the most common, which is the most frequently occurring words. And I see that the word she occurs 10 times, it occurs 8 times, was occurs 6, and so forth. This is brilliant. This is a way to count things very, very easily. that would be nice for us to do in our log analysis, right? All we need to do in our script is create a list of URLs from the log file. Once we create a list of URLs, we can count the frequency in that list. So to do this, outside of my loop of reading the text file, I create an empty list. This is called URLs. And then as I read through the data, this is the loop, this is the stuff that happens for each line of the file, I'm appending the URL that was extracted with the regular expression to this great big list. That's it. Once I've done that, I can use a counter dictionary to count the occurrences of URLs. And so I define another function here where I create a collections.counter dictionary, and then I update from that dictionary the URL list that I pass into this function. And we can then print out the most common URLs and how many of them by looping through that dictionary. And we have a winner. Okay. Not too bad. So if we run this thing, and I can show you how this works, we will get a count of URLs out of that log file, how many times they occurred, by using a combination of regular expressions and a counter dictionary to count the instances of URLs that have been extracted out of that log file. And to prove to you that I'm just not fabricating this, because I'm not, let's pull up the script, okay? And inside of the script, which is called Squid Log Analyzer, you can see, yes, indeed, here's my giant regular expression. Here's my URLs list down here. And here's me appending the URL data as I process the file into that list. And then down here, here's me calling my method called show URL counts. And I also have one called show HTTP methods, but I'll comment that out briefly. And if we run that script against our log file, and I can run it with // and the reason I can run it with // by the way is because it has the shebang line at the top here. You see this? Okay. / squid log analyzer access.log, and out pops a URL count nicely, and it shows that we processed 803 lines of text. 44 of those were wireapi.reuters.com, 26 were reuters.demex.net. I guess I had a Reuters fascination. There's a lot of google.com in here. That's not surprising in anybody's network, etc., etc. Right? So this is a really nice way to do some very effective log analysis, right? What about data categorization? So there is a data structure in Python called a dictionary. And a dictionary is the same as what in other languages is often called a hash table. And in short, a dictionary stores data as key value pairs. Now, we just saw in the case of a counter dictionary that the key value pairs were individual words plus the frequency count as the value. But we don't have to create dictionaries like that. We could use a string value for a key and then use a list of items that belong to that categorization, that belong to that key data, right? So one of the slight challenges in doing this is that when we use Python dictionaries, if we access a key that does not exist in the dictionary, it actually throws an exception. It will throw an exception and it will error out your script unless you catch that exception, right? This is a very simple example on the screen to define a dictionary and that you try to access a key that does not exist in that dictionary. And when I try to access that key, I get a key error exception. That's a little bit annoying and makes us have to use additional logic into our scripts to handle that issue when we are trying to categorize data. If the logic for categorizing the data is to have the key represent the category name and the value associated with that key to be a list of other items belonging to that category, we can use something called a default dictionary. The collections module, again, has this concept called a default dictionary. It's implemented as a function called default dict. And what that does is that if you try to access a key that does not exist in the default dictionary, it will automatically create a key value pair for you and initialize the value to the return of a function that you define. So the way to do this for our example is to create a function, and here we've used a lambda. Lambda is borrowed from calculus, and the function just returns an empty list. And so we're saying A equals collection.default dictionary, lambda colon empty list. If I try to access the key of Joff, and Joff does not exist in the dictionary, it will create that key value pair, and the value will be set to an empty list, okay? And then you could just append to that list. And so this greatly simplifies the logic for data categorization. So the second part of the exercise is, can we categorize the URLs based on the HTTP method used to request that particular HTTP URL? To do that, we need to create a default dictionary for the HTTP methods. So up here, outside of my loop, I'm creating a default dictionary with my HTTP methods variable, and the lambda function there returns an empty list, which would initialize a key value pair for something that doesn't exist. And then down here, I am extracting the HTTP method, and then I'm looking to see if the URL is in the current method dictionary entry, and if it's not, I'm appending it, thereby categorizing individual URLs to the method used inside of our log file. Again, relatively small amount of code, high level of conceptual understanding needed, but extremely powerful result. Now, to print out the result, well, we could loop through using a method called show HTTP methods, which we have to custom write, and then just use some format strings to actually print out the URLs that belong to each method. This is a little complex, and I did only print out about 3 or 4 URLs that belong to the method so I could shorten the output. But it does get to the result that we're needed, and the ultimate output is going to look something like this. There are 283 instances of using the verb connect, and the URLs associated with that connect verb are as follows. PayPal objects, Reuters, BidSwitch, Mode AS, etc., right? ADS. So we get very useful analysis results by following this kind of recipe, okay? And you have all the code, so I can go ahead and edit that squid log analyzer again, take out the part that doesn't print the methods, just uncomment that here, show HTTP methods, rerun the script, and you'll see that it indeed produces that same result. And so collaboratively, what we've done there is used a combination of very powerful regular expressions to parse out this data in this log file and then use the combination of a default dictionary for categorization and a counter dictionary for pure counting to give us a very detailed and useful breakdown of some of the data that's in that SQUID access log. And you could think of probably many examples in your day-to-day life where you could take this script and modify it to your own purposes, right? And you could just follow the example, right? Depending on the log file that you're processing, you're going to have to redefine this regular expression. And then you're going to have to go further down in the script and change a little bit of the logic in here and, you know, customize it to your liking. But the basic skeletal outline, if you like, is there for you to do some really quite sophisticated regular expression processing of log files in Python. And I think that's a very useful skill to have. Again, as I said earlier, I use regular expressions on an almost daily basis. I combine regular expressions in particular with Python scripting frequently. And the reason I do that is because I can write a Python script very, very quickly to give me a very powerful result in a small amount of time. And that's compelling for me. And so I would recommend, you know, that you do similar things because, you know, Python, you know, gives you a lot of very high level powerful ability to actually do that, right? And that, my friends, brings us to the end of the show. It is 3:40 p.m. US Eastern time here, so we are 20 minutes early, but that's about when the show finishes normally anyway. I hope that you have accepted that regular expressions are a very powerful facet of what you can do in our industry, a very universally applicable analysis technique that can be used in multiple contexts to your advantage. And I really hope that you study it further and that you take on board many of these examples and integrate regular expressions into your life, because you will do things more efficiently once you start thinking in this fashion, and it is extraordinarily helpful to do things that way. Now, right about the time that I taught the first class of 2022, we had our friend, and it always happens at holidays, right? We had our friend Log4j come about, right? And I said to everybody, hey, you want a quick regular expression to find Log4j attempts in all of your web server logs or all of your any logs? Here's one: find/var/log/name star.gz, pipe it to xargs, zgrep it, and give it the -p for a Perl compatible regular expression, and look for JDNI : LDAPS or RMI or DNS, and boom, you will extract all of the Log4j activity in any of your logs with that expression alone. Okay? I'm out of breath. I'm out of breath, everybody. I hope you enjoyed your day. I always enjoy teaching this. I think, frankly, I think this is some of the most powerful knowledge that you can acquire in this industry. And I sincerely mean that. I want you to take this on board and really think about this, because you can do some incredible work with some programming or scripting languages combined with regular expressions in particular. So, you know, do it, okay? Okay, everybody, that calls it a day. The recording will be available to you. Folks are fairly quick about getting the recording back. It'll come back in the resources channel, I believe, in Discord here. You do have the zip file of the materials. You do have the cheat sheet to take home, study that stuff, rewatch the class, adopt regular expressions into your lifestyle, and go forth and do good things, as we like to say at Black Hills. Thanks so much for having me. Thanks for being a part of the class, and I will see you next time.